For the second part of the OGB-LSC large-scale challenge session, we're going to have a special session. We have two main contents. The first one will be the invited keynotes by the prominent researchers, and the second part will be the panel discussion on the next step of graph machine learning. So for the invited keynote, we'll have three great speakers. The first speaker will be Victor Prasanna from University of Southern California, and he'll be talking about the intersection between the graph machine learning and the system. Second speaker will be Marinka Zitnik from Harvard University, and she'll be talking about the application of graph machine learning to biomedical domains. And thirdly, we'll have Larry Zitnik from Facebook AI Research, and he'll be sharing with us his experience on creating impactful benchmark datasets. And after that, we're going to have a panel discussion among these four leading researchers of graph machine learning. The first panelist is Yizo Sun from UCLA, then Zhen Zhang from NYC, Shanghai, and Amazon AWS, Shui Wangji from Taden, and Jane Tang from Milan. So we are very excited to have these two sessions today. Okay, this concludes my brief introduction of what we're going to have today. So we can move on to the keynotes.
Yeah, Victor, please feel free to share your screen. Yeah. So good morning, everyone. I guess in the West Coast, and good evening for all those in Asia, and good afternoon for those in Europe. So it's my great honor to introduce Professor Victor Prasanna from University of Southern California. So she will open the keynote session this morning. And Victor is a professor in both EE and computer science in University of Southern California. And his research interests include high performance computing, parallel and distributed system, cloud computing, and the smart energy system. And he received his PhD from computer science from the Pennsylvania State University. And he has been served in many steering community of impactful and influential international conference, as well as editor-in-chief of many IEEE and ACM journals, such as the IEEE, the editor-in-chief for IEEE transaction on computers. And he is also a fellow of IEEE, ACM, and AAAS. So without further ado, let's welcome Professor Victor Prasanna for today's keynote. Yeah, please go ahead, Victor.
Thank you, Ishwar, and then also the organizers of KDD Cup for inviting me. I'm pleased to be here. I'm calling in from India. It's around 8:30 p.m. here. It's also a big day in India. It's the Independence Day celebration. So I think a lot of activities in India at this time. So in this talk today, I will focus on accelerating graph machine learning, just to kind of look at what are the issues we face and look at some implementations, look at some new technologies in this context, and also make some comments about possibly how we may build a system, that scalable system for very large scale training as well as inferencing. There's quite a lot of research in this area, as you all know, in the last few years. So my goal here is to kind of highlight from a computational perspective, what are the challenges and what are the opportunities for us to be able to accelerate these kinds of computations. So the outline of this talk, I will very, very quickly go through from a computational perspective, graph neural networks. I think everybody in the audience, I'm sure, knows about it, just to keep this talk complete. Then I'll talk about some of the challenges in accelerating, what are the issues we face in terms of communication, computation, in the context of this training as well as inferencing. I will also talk about some emerging architectures, FPGAs, heterogeneous architectures in this context. And then I'll go through one example result, which is about using FPGAs and processors for accelerating for a full graph inference problem. And then finally, I will have some comments as to where this kind of line of research is headed in terms of being able to trade off accuracy and also look at the computational issues that comes there in the context of designing these models as well as accelerators, so that we can get a very high performance distributed platform. So a lot of this work is joint work with my team, my students. I've listed here a couple of papers that are relevant here. I'm not going to go through a lot of technical details. I'll keep this discussion to be at a fairly high level, but I'm happy to go through any specific details, questions you might have towards the end, as well as take this offline with any of you who may be interested in this space. Very, very quickly, GNNs, what we are trying to do here is, given this graph, we are trying to find a vector embedding for that representation by using a feature representation. So we would like to get a low dimensional representation for this. And then once we have this representation, we can solve various downstream problems, link prediction, for example, node classification problems. So if we are able to produce this vector embedding, we can solve many downstream problems very efficiently, perhaps sometimes very quickly as well. Sometimes some of these problems are computationally challenging. We may be able to get better solutions or faster solutions for these kinds of downstream applications. As far as these problems are concerned here, they take quite a bit of time, both from the perspective of training as well as from inferencing. The graphs are very large. We're looking at the training time that could be in the range of hours to days. And we also would like to do these kinds of operations very quickly in real time. There are latency sensitive applications where parallel computing or high performance computing can be very useful and be able to solve problems in reasonable amount of time. So from a computational perspective, so I'm going to kind of get away from all the details from a machine learning perspective. I'm just looking at it from what happens in these models. What are we trying to accelerate in this context? So in general, we have this various layers in this network. I denote this by the number of layers we have. So we are abstracting these various models in the community by using these parameters. This specifies the number of layers you have and what happens inside each one of these layers. There is some kind of an aggregation that takes place. There are various matrices I've shown here. For each layer, we could have a particular matrix. This is typically a sparse matrix. And then we have these weights that are applied on those representative after you perform the aggregation at those individual layers you have. So we're looking at these layers. That means you go from layer by layer, these various layers, till we go to the output layer here. And the basic operations we are doing here, we are aggregating by using this sparse matrices given to us. There are various ways of specifying these sparse matrices depending on the particular GNN model being used here. There are various the functions that is used here as part of the aggregation here. All this is part of the GNN model specification we have. So there's a whole lot of research in this space, which we are not going to go into in this talk. Our focus here is that given such a computational requirement, how do we accelerate these computations by using some of the emerging technologies in the market? So on the right-hand side here, I just want to reiterate one important point here that is distinguishing. What is the size of these models? The models are represented by the number of layers you have here and the weight matrices that you have here, which are used for the feature transformation. And typically here, I've just shown here what happens in a typical model. For example, if you look at a graph stage kind of a network, the size of this model is not very large. We're talking about hundreds of kilobytes, maybe megabytes. That is typical in these applications. Of course, there are also deeper models where the number of weights is going to be very large in those applications. So abstracting these problems, our specific problem here is that we are, for each layer, we are doing a particular kind of operations, which is aggregating by using this matrix that is provided for that particular layer, and then doing this weight transformation here by using that weight matrix for that particular layer we have. So the operations we are doing here are doing this sparse dense matrix multiplication, and then also followed by a weight transformation, which will be a dense matrix multiplication that is used by using this weight matrix you have here. I've given some comments here in terms of what happens in these applications, what is the typical sizes we have in these transformations, so that we can understand how the cache will perform, how the on-chip resources on the GPU, as well as the Fpgas, for example, can be used in those applications. These weight matrices are not very large. What it means is that if you can play around the particular architecture, we can save these weight matrices on the on-chip resources that can give you high performance by reducing the traffic to the memory or to the communication cost in those implementations. So if you look at the GNN acceleration, we can look at the training as well as inference. If you're looking at training, we need to get high throughput implementations here as we are having large number of mini batches. As we go through a particular epoch, we want to be able to complete those operations very quickly. And then our challenge here is that we want to be able to get this high throughput, given that we have very large graphs. Graphs are very huge. We're talking about hundreds of billions of vertices and edges in these kinds of graphs here. And these operations typically on a GPU platform that is state-of-the-art platforms that is used today, they can take a significant amount of time, and our intention here is to reduce those kinds of training times. When you go to the inference here, for the given model, we want to be able to accurate good parallel implementation that also preserves accuracy. And latency is very important in these applications, particularly if you like to support real-time or latency-sensitive applications. So we want to make sure that we can solve these problems in the range of tens to hundreds of milliseconds, for example, in the context of a recommendation system. That should be the kind of response times that we're looking for. Also, that we need to sample a large number of nodes. That also adds to the complexity here in terms of the amount of time you spend in preparing for these implementations. This is just a high-level view of what happens in the training. It's a kind of a serial version of it, meaning that I do, in this context, some graph pre-processing. Following that, we do graph sampling to set up the particular the adjacency matrices I talked about earlier. Then we load those features. Then we do feature aggregation and feature transformation, sparse matrix multiplication, followed by dense matrix multiplication. We repeat that for the number of layers we have, and then we compute the gradients, and then we propagate the errors back in the reverse direction. I've shown here the typical computations you perform here. There is significant amount of graph access, irregular memory access is coming into picture. Also, some of these operations are not specific to the kind of operations we are used to seeing in the context of CNN operations. Quite a bit of memory transfer that takes place here. I will go through an illustrative example here at how much memory transfer takes place here, followed by sparse as well as the dense matrix multiplication operations. That's kind of the big picture of what happens. Now, if you look at this implementing this in a parallel format, I've just given a simple abstraction from the perspective of what happens in a parallel system. We still do some initial graph pre-processing. Afterwards, there are a number of parallel activities we can create here, which corresponds to operating on those mini batches in parallel, the sampling as well as aggregation and transformation. And then we compute whatever we want to propagate in the reverse direction. That's what is happening in the back propagation. And then we synchronize. And then we share the values of the gradients across all the processes we have, all the processors we have here, and then we do weight updates here, and then repeat this here for the various iterations you have, and then repeat this across all the epochs we have to cover all the vertices you have as part of the training here. I also put some question marks here. Again, there is a lot of opportunity here in how do we implement them on a parallel machine. It is not necessary for us to be able to take all of these operations in a synchronous manner. So one of the challenges we face here is that when we do this sampling here, different parallel activities you have might have different amount of workload based on the degree distribution of the vertices you have in the graph. So we need to be able to do load balancing here. So at this point, by looking at these operations in a synchronous fashion, we may be able to do some of these operations load balance and get scalable and high performance implementations. Just to get a sense of where the time is spent in these implementations, I'm just showing here what happens for two different data sets. And then if we implement the training here, what for the various steps I talked about in terms of sampling, in terms of feature aggregation, feature transformation, and the various other bookkeeping operations we do there. So I think the important point to notice here is that a lot of the time is spent here in terms of being able to collect all those sampled graph information and then doing those feature aggregation, which is a sparse times a dense matrix multiplication operation we do here. And part of the critical challenge here, the critical bottleneck here is in terms of loading those features from the external memory or the DRAM of the systems into the local memory of the GPU or the Fpgas or the accelerator before we perform those matrix operations. So there's a significant amount of overhead that comes into picture. So the conclusion here is that while we talk about these linear algebra operations, the sparse and dense operations, It is really the bottleneck here in the systems is in terms of accessing this graph, very large graph structures, preparing for us to be able to apply those linear algebra operations before we iterate that across the various layers you have in the system. So I've kind of summarized here, looking back at what happens in GNN computations and what happens in a typical deep neural network training and inference. I've just kind of tried to summarize here the observations in terms of the size of the model. The GNN models tend to be small compared to the number of weights you have. For example, in CNNs, it could be in the range of megabytes. Typically, it is hundreds of kilobytes in the context of GNNs. The amount of data that you use for inferencing, when you sample this for a given vertex, you want to perform the inference. If you compute the neighborhood inside that, it could be quite large compared to what happens in the context of CNN models. The images that are used there are fairly small compared to the size of the neighborhood that we use for in the context of GNNs. Also, the computations we are performing, we do sparse computations, unstructured data that we have here, whereas in the case of CNNs, the computations are well structured. There's quite a lot of data reuse that comes into picture that gives rise to a lot of optimizations we can do on cache-based systems, for example. So we also look at small matrices here. The matrices are not large compared to the kind of matrices that we do. For example, if you use image to column or a kernel to row kind of techniques that are used in the context of DNN acceleration here. So, also one important point is that when we implement this parallel training methods for DNNs, a significant amount of the research is conducted to be able to reduce the synchronization time across the various parallel activities you have the system when you share the gradients across the various processes, parallel processes you have in the system. So in the case of the GNN models, because the model is quite compact, we're talking about hundreds of kilobytes, the amount of time you spend for those communicating those gradients or the back propagation information across the various parallel processes you have in the system is typically negligible. So we don't have to really focus on that as an optimization to implement this operations. So very quickly here, so we are focused here in looking at some of the newer technologies in the market. As you know that there are a lot of new computing platforms are coming into the picture in terms of application-specific accelerators, Fpgas, which is something that I will talk about in some detail, CPUs, GPUs, all connected to various interconnect technologies, as well as some of the advanced memory technologies that is coming in the market. So very quickly here, we are looking at implementations by using Fpgas. A lot of advantages we'll go through that we have this configurable logic. That means you can define what kind of operations you want to implement. For example, you can define systolic arrays on these implementations by using these fine-grained computations as well as the DSPs available. Also, the on-chip resources available, the block RAMs, so they have static RAMs available on these devices, which can be effectively used to store those feature vectors and the weight matrices that can potentially give to very high performance in these implementations. Also that these devices have extremely high on-chip bandwidth that can also be effectively used to be able to do this layer-to-layer connections you have in them that can be efficiently implemented. And also when you go from layer to layer, there is a moment of, when you perform this computation, certain data shuffling that needs to take place. That requires quite a bit of high bandwidth connectivity, and that is supported on these devices, which makes these devices to be very attractive for these implementations. I'm just giving a summary of state-of-the-art devices in the market coming from Xilinx as well as Intel. These are very powerful devices, typically having billions of transistors, giving rise to tens of thousands of DSP processors, also quite a bit of on-chip memory as well as logic available on these devices, which makes these devices to be extremely powerful and very attractive for these kinds of application-specific acceleration for these applications. Also, as we going along in this direction here, there are some newer devices coming in the market. For example, Xilinx has a complete heterogeneous architecture on a single device. You can do data parallel programming. You have a traditional CPU multi-core programming, as well as Fpgas, all on a single device that gives you very high performance in terms of being able to transfer the data and to be able to do large number of operations per unit of time in these kinds of advanced system on chip devices. One important feature which makes these devices also very attractive, these heterogeneous architectures coming in the market, is also the what is called the cache coherent interconnect. That means we can take this FPGAs, we can take the accelerators and let them share the main memory of the system where the large graph is going to be stored. That makes it very attractive in the sense that when you're doing this feature loading, which is very expensive in traditional implementations, those kinds of operations can be very efficiently performed because you can keep the data in the main memory of the system itself and access that from the accelerators, which can give rise to very high performance in this implementation. I'm just making a summary comparison here in terms of technologies available for acceleration, comparing FPGAs with the multi-core GPUs, and there are some newer accelerators coming in the market. This is one of the newer machines specifically designed for accelerating AI and machine learning applications. So these devices have extremely high performance. I won't go into the details here. In terms of the on-chip resources, number of multiplication operations per second you can do on these devices, the data bandwidth available on these devices, number of memory controllers you have, as well as the on-chip memory that you have on these devices that can be used for storing the weight matrices, for example, in these implementations. Also, when you build these deep pipelines for FPGA implementations, it is possible to store all the intermediate feature vectors on the device itself, which makes it very attractive in the sense that I don't have to go to the main memory and come back all the time. So I can implement, for example, a 5-stage pipeline for us to be able to take a 5-stage, 5-layer network. All the intermediate results can be stored on the device. So that can give rise to very high performance in these implementations. So moving along, so from the perspective of using these technologies, what really makes this problem challenging compared to the traditional acceleration problems we have seen in the context of machine learning and deep learning applications? These data sizes are very large. We're talking about billions of vertices and edges, tens of billions of edges coming into picture here. Obviously, they do not fit on the on-chip resources, FPGA or the processor or GPU on-chip memory you have. These have a lot of random memory accesses, very poor data reuse in these applications, which makes it very difficult to be able to effectively use the on-chip memory in these devices unless you carefully design a specific memory system for these applications. I talked about the load imbalance problem. As you sample and create these mini batches, different mini batches can do different amount of work based on the degree distribution that is there in these mini batches that we create. And also that there are two kinds of operations, the sparse times dense as well as the dense matrix multiplication. These two are very different computational kernels, and then pipelining them to build that into a stage can also lead to pipeline stalls in those implementations. Also that our interest is to look at various GNN models to be able to implement them. So various models have various features. Some of these models, for example, the graph structure is statically defined. Some of these models, you can dynamically define what those graph structures are. We want to be able to support all of those kinds of GNN models by using one scalable distributed platform for us to be able to implement it. Also, there are specific concerns in terms of full graph versus sampling-based approaches versus training versus inference. There are also some specific optimizations we can do, which can give rise to different challenges in those implementations. So one general technique that we have proposed, which you can look at the details that is published here, what we call the graph processing over partitions. This is a particular technique that we developed in terms of looking at how do we look at very large graphs, and then we are doing parallel computing on them, and how do we optimize the communication in that, how do we optimize the computation in that case, also to make sure that the external memory accesses, the DRAM accesses are optimized in that context. So this is specifically using a particular model called the scatter-gather model. That means you take information from the various vertices that are contributing to the input layer 0 of the GNN model, and then use that information to be able to then apply those to be able to apply the aggregation function, and then go stage by stage by storing the local, all the weight matrices on the FPGA devices or the local memory available on these devices. I have got a lot of details here in this diagram. What is important here is that we can structure this computation so that we can support various training methods, various the GNN models, also various techniques in which it is not necessary to synchronize all of these parallel activities we have. So we can do some asynchronous execution, which will also help us from the perspective of the load balancing, so that if you have different mini batches taking different amounts of time, so we can kind of use them in an asynchronous execution by using these buffers or the bins I talk about here, that can give rise to high performance in this implementations. So moving along, so just an example of a result. You can find these results in a recent paper that is published at the FCCM conference, which is looking at heterogeneous architectures, FPGAs, GPUs from a computational perspective. We call this the Boost GCN framework. In this context, we use the target architecture consisting of multi-core FPGA connected through the PCI Express interconnect, and then also having a very large DDR memory where the graph data is stored in this as a given input graph is stored in the DRAM. So just quickly here, this particular architecture is optimized so that we build these pipelines. Where we build the pipeline, that means we look at the complete layers you have in the GNN model we have, and then we allocate the local resources, and then we build this feature aggregation module and feature transformation modular, which is a systolic array that we design on this FPGA device here. And all these operations are pipeline, as that means that based on the available on-chip memory we have, we can buffer those layers we have, and then we can build multiple pipelines here. I've shown here example of parallel pipelines you can build here, and that is interfaced to the memory controller to get very high performance. There are a number of challenges here. For example, how do we improve data reuse? How do you make sure the memory access costs are minimized? What kind of data layouts to be used? What kind of partitioning to be performed? All these are all discussed in detail in that paper. There are some interesting optimizations we can do in this context to get very high performance, so that all these pipelines can operate in parallel without stalling, so that can give you very high performance in those implementations. Just quickly here, some experimental results. We implemented this on a Intel Statics, another state-of-the-art devices by using external memory here with typical bandwidth that is available in these kinds of platforms is around 70 to 80 gigabytes per second. Our goal here is to be effectively use this complete bandwidth, so that the significant amount of the feature loading time that I talked about earlier, that is reduced in these implementations. So we used a number of baselines here, PyTorch geometric implementation or the deep graph library from Amazon. We use the usual data sets that is available in the market. And then I'm just showing some example here of the data sets that we used and the typical values, the metadata for this various data that we used here. Just concluding this here in terms of what is the performance we can get. So if you compare against the CPU implementations, we can get significant performance by effectively using the FPGA devices and the on-chip, particularly the on-chip static RAM on these devices you have here. Also, compared to a GPU, we can get again significant performance improvement. Quite a bit of the data loading time can be reduced because of the shared memory we have in the systems. Also, we can build these pipelines and schedule them so that there are no pipeline stalls coming into picture. That gives rise to very high performance in these implementations. So I've shown here the actual results here, which was just recently published here by using this FPGA here, and then the typical speedups you can get here compared to the CPU and the GPU implementations, which are some of the state-of-the-art implementations in the literature. So let me try to kind of conclude this line of thinking as to where we are headed. So we are interested in building a more general framework. By general framework, I mean to be able to use the target platforms consisting of multiple nodes, where each node consists of local memory, processors, and accelerators. Could be, for example, based on for FPGAs or whatever accelerator technologies coming into picture. So we want to build a system where the user comes, specifies the model that is to be used in terms of some high-level metadata, specifies the target hardware that we have in terms of number of nodes, number of the memory channels available, some kind of a high-level metadata, and then we want to be able to get complete design which runs on the accelerators or on the FPGAs, and a program that is running on the CPU and that is coordinated across the multiple nodes we have in the system. That's kind of the big picture of where we are headed. I'm just giving some high-level view here. What are the challenges we face? So I'm looking at it here in terms of what is typically possible in these devices, what kind of bandwidth and latencies are available in the market today, and using that information to be able to come up with what performance we can get. The distributed algorithm that we are implementing, we do both data parallelism and model parallelism in this here across the various nodes we have inside each of the nodes here to be able to do model parallelism so that we can effectively exploit the accelerators in this context. I'm showing here, if you are able to implement a system like this, which is something that we are working on, where we show that it's really, again, this graph sampling time still is a significant time. The challenge here is that when you go to very large platforms like this, even though we have these high-speed interconnects here, a lot of the time is spent in terms of looking at this data across the various nodes we have and to be able to fetch the data as opposed to looking at inside what happens inside the processor here. So this data time has been reduced, whereas this time becomes a dominating time here in terms of what happens across the various nodes you have in the system. So that's where I think this performance still is bottlenecked by this significant time in terms of accessing, creating the input sample graphs, and then feeding them to the various nodes you have, the accelerator nodes you have in the system. So in this context, there is an area of research which is an emerging area. I think some in the audience here will also know about it. Is it possible that we can define alternate GNN models in which are computationally kind of efficient from perspective of how do we map them into target parallel architectures we have? So we are doing some work in this context. We did have an archive publication here, which is looking at decoupling the number of layers you have, and also decoupling in terms of decoupling that from the kind of the sampling we do in that context, so that some accuracy is preserved. At the same time, there is some computational efficiency in terms of, for example, data reuse. So if you look at models such as GraphSage, the amount of data reuse or the amount of computation intensity you have in terms of how much data you bring in from the features and how much work you do based on the data, that is less compared to by using these kinds of decoupled models I talk about here, where you do some kind of a model architecture co-design, where you try to preserve some accuracy requirements from machine learning perspective. At the same time, the model that you have is computationally efficient to implement in terms of using the various performance metrics coming from a parallel computing perspective, for example. It's an interesting area of research. So we have some results in this context here, which is discussed in this paper, as well as ongoing results in my group, where we do these kinds of a co-design optimization so that existing architecture, whether it's GPU or FPGAs or heterogeneous or other ASIC accelerators, could be effectively used in this context. So let me conclude this talk. So I kind of looked at from what are the challenges comparing the GNN training versus the traditional deep machine learning acceleration. So weight sharing update is not a key issue in the context of GNN training acceleration. One of the challenges we face here is the low computation intensity, primarily because of the sparse matrix computations that come into picture. And this also leads to irregular memory accesses, which really becomes a dominating factor in these implementations in terms of creating those feature vectors, those subgraphs to be loaded into the FPGA or to the GPU architecture we have. So what we showed here is that if we use FPGAs tightly coupled with processors, it is possible to get significant performance improvements by effectively using this on-chip memory, as well as reducing the traffic to the memory we have. We can also use heterogeneous platforms. I didn't talk about that in detail today. Some of the work we presented that talks about how to use both the CPU and the FPGA to be able to get very high performance. You do the sampling on the CPU and then convert them into the sample graphs, have some internal representations which are compact, and then feed them to the FPGA to be able to perform those pipelined operations for the various layers in those implementations. One interesting area of research, which I talked about very briefly, is this idea of model architecture co-design. Designing these models to be effective in terms of communication, in terms of computation intensity, in terms of data reuse, also minimizing the number of external memory accesses, irregular memory accesses. There's an interesting area here, which is a co-design between the machine learning community and the architecture or the parallel computing community that can give a very high performance implementations. So let me stop here. I believe I'm a little bit over time, so I can take any questions that may be.
Yeah, thank you, Victor. Thanks for the exciting talk. So it will be very attractive to try your, I guess, frameworks or architecture to OGB dataset, which are pretty large this year. So yeah, So given that all panelists can actually ask questions through microphone, so please feel free to open up your mic to ask questions. For attendees, please feel free to post questions in the Q&A chat box. Yeah. And Shuang, do you want to ask question directly?
Yeah, I typed my question there, but just this is request for comment. So this is mainly about the computer architecture, but I'm wondering, Victor, can talk a little bit about the prospect of federated learning or graphs?
Right. Yeah, I think that's a very good question. So one of the things that we're doing here, the general architecture we are building, so we can take some of the federated learning computations you have in terms of the parallel processes I talked about. So our big picture here in the general compilation framework we are providing here. So if your computational framework is, let's say, federated as opposed to the purely distributed fashion I talked about here, so we can also map those kinds of computations into this general platform I'm talking about. The compilation framework will be different, but the bottom up, the architecture features are captured in the design space exploration tool that we are building. And then in that context, we can specify what the computations you want to perform. And you specify the code for each one of those computations. And then we do some partitioning here, which is manual in terms of what happens on the processor, what happens on the accelerator, and how the coordination takes place. That portion is not completely automated.
Wonderful. Thank you, Victor.
Any other question? Okay, so I have one question, Victor. So assuming that you have very large graph, say 3 billion users and tens of billions of links, which are how to put it? It's streaming links, like update actively every day. So if you want to do some GN training, do you think or do you share any thoughts on how to leverage your architecture optimization or framework to speed up this training process, GM training? Yeah.
Right. So I think if you have a streaming data or what you refer to here as some kind of a dynamic graph.
Mm-hmm.
So one question that we are looking at it from a perspective of dynamic graph update problems. So rather than start the whole process from ground zero and recompute all the embeddings, for example. So can we make some incremental changes? Suppose that happen for a real problem you have, and then can we kind of incrementally update some of those vectors, for example? So we are looking at these kinds of problems. For example, if the initial weight matrices have been defined, the model has been trained, and then you make a small number of updates to the graph. And then the updates could be in terms of links, or updates could be in terms of adding some new nodes. Updates could be in terms of the initial feature vector values you have. So we are looking at problems of that nature. And then how do we effectively map them onto accelerators? So one of the important problems that comes here is some of the graph analytics, incremental graph algorithms could be useful here. But the challenge we face is that for very, very large graphs like we have, the increments could be kind of may not be uniformly distributed across all the nodes you have in the system. So there are some overheads that comes into picture. So this is an important problem. We are looking into it. I don't know of any initial results that can do these things very quickly.
Yeah, thanks for sharing this. So any other question? One last chance. Okay, thanks again, Victor. Thanks for joining us this morning, and thanks for the great talk. And I guess let's welcome the second speaker of this session. So Dr. Marinka Zitnik. So Marinka is an assistant professor in Biomedical Informatics Department at Harvard University. He is also an associate member in Broad Institute of MIT and Harvard, as well as a member of the Chan Zuckerberg BioHub. And she has her research interest has been on graph machine learning, which has generated interest of government, academic, and industry researchers, and has put put many practical tools in the hands of industry practitioner. And some of her methods are used by major biomedical institutions. For example, Baylor College of Medicine, Stanford Medical School, and Massachusetts General Hospital. So I guess today she will talk about a new graph machine learning benchmark for bio or medicine. So I'm not sure, but Marinka, please go ahead. Thanks.
Thank you for this kind introduction, and thank you for inviting me to this workshop. I cannot share my screen now because there's other participants sharing the screen. If you can give me access to that, would be great. Okay, thank you. Let me start sharing my screen. Okay, great. So I hope you see the screen. Thank you again for this kind introduction and for inviting me here. I very much appreciate the KDD Cup workshop this year, and I've been closely following the advances and the research that has been done, and there's lots to learn. And thank you for all the efforts in organizing that. So today I will talk about few-shot learning for biomedical discovery. It will be a slightly different talk than the one before me, but I hope that you will enjoy it and also take and learn something from it. So why are applications of graph machine learning or machine learning more broadly for biomedical discovery so challenging? So today, the key challenge that I'll be focusing on is that for problems that are really novel, that are at the frontier of scientific research, that are at the frontier of biology and medicine, it is that we have very, very, very little or no label data at all. And so that's an issue because most of recent breakthroughs in ML have depended on lots of label data and having access to large, diverse data sets that are richly annotated in order to really then capitalize on that and leverage those data sets and achieve broad generalization. And so that is challenging because when we work on problems that are at the frontier of science, they're typically very poorly understood. And that's why they're interesting and they are new phenomena. Therefore, achieving that models generalized to these new phenomena can be very hard. And prevailing methods, even in graph machine learning, still require abundant label information. However, as I said, labeled examples are scarce for really novel problems in science and in biomedical discovery. And so examples of such problems are questions related to novel drugs from scratch, then modeling and diagnosing emerging diseases that have never been seen before, trying to address problems that relate to emerging pathogens, or trying to find good treatments for patients that are otherwise very hard to diagnose because they might have diseases that have never been seen before or somehow does not fall into medical knowledge. So these are all examples that are very important, crucial problems, really novel problems in science and medicine, yet there are very little label information data available for them to be able to train kind of some of the most powerful GNN models that are out there. So the way to think of it is what prevailing methods assume is that they assume that we mostly have these richly labeled annotated graphs where most of the nodes are already annotated, and the goal is to leverage that information in order to annotate the remaining nodes. But what really happens in the real world is that we have this vast dark matter, many nodes that are gray. We don't really know anything about them at all. There might be genes, proteins, and other kinds of structures that science care about. And there are very few entities that are well understood and for which labeled data are available. So how can we leverage that effectively? That would be, and how can we learn in those really harder settings that are indicative of real world situations we encounter in biomedical discovery. And so today in my talk, I will cover the question of few-shot learning for graphs, and then I will also describe an important application of that algorithms that I will first outline, and then conclude with opportunities for novel methodology development in the area of therapeutics and what data sets are available for that. Okay, so let's start. So few-shot learning for graphs, and then our problem formulation will be the following. I'm highlighting a method that is called GMeta, that is a general graph machine learning framework for meta-learning. And the idea here is that we will assume we'll start with the simplest setting, which is that we have a single graph G, and that graph G has some nodes and some sets of labels that we want to predict. And so the question then becomes, in this single setting where we have a single graph and disjoint label set, we want to design a meta learner that will be able to classify a label set, a blue one, Y sub star, that has not been seen during training time. So that it would be the label set that during training time was not available to us. It represents labels that we have never seen before. And we want to get such a GNN model that can quickly adapt to this blue label set, given only very limited amount of information about it. But lots of information might be available about some other label sets here denoted as in yellow color. So the way to approach this task, or the way the overview of GMeta is the following. So we adopt a well-known meta training, meta testing strategy that is a well-known strategy in meta learning, and we define and during the meta training phase specify a large number of training tasks. Each training task is a task where we ask our GNN model to use only a handful of labeled examples. So here's just a case where 2 labeled examples are used per class in order for the model to quickly train a node classifier that will be able to label the remaining nodes in the graph with those labels. And so during meta training time, we would specify a large number of training tasks. Every training task is defined on the Y label set. During meta testing phase, we need to build a classifier that would distinguish between nodes that are annotated with a new label set, Y star, and the issue is that we have only 2 labeled examples for each label available. And so what GMeta allows us to really effectively leverage information and structural information from graphs that is available in the meta training phase in order to quickly adapt and produce the classifier for predicting different shades of blue on this new label set Y star. And the key idea behind that is that we will use structures that we refer to as local subgraphs. So every task that's either in the meta training phase will be defined as a distribution over subgraphs, and subgraphs will be used but in GMeta to learn a global set of parameters that are then transferred from one task to the other. So for each task, we define a subgraph signature function that is a signature of a given task. And that function maps the structure of subgraphs that enclose a small number of labeled examples in that task. And that structure is then being transferred from one task to the other. So there have been a few short learning strategies proposed there that rely on graph level signature functions. And so why those methodologies are not particularly successful is because it's very hard to assume and learn reliable graph level representations for graphs that go beyond graphs of trivial size, like molecular graphs that are typically very, very small. And so then subgraph level signature functions are a much better way to capture local structural information about a small number of labeled examples. So the idea is then, if we start with the input graph where we have a small number of labeled nodes, we extract local subgraphs that are defined as enclosing subgraphs of some radius K around labeled nodes, and we embed those enclosing subgraphs around target nodes to obtain subgraph level representations. They constitute our signature functions, and they are then fed into a prototypical loss. And so I will not go into detail about how to get subgraph representations, but we have an approach that is called subgraph neural networks, or SubGNN, that allows us to really learn subgraph structure very well, capturing all the different aspects of subgraph topology, which go beyond standard neighborhood principles and structural similarity. So it's possible to theoretically motivate the use of subgraphs, because what we did, we studied what is the influence of nodes in the neighborhood and local vicinity of the target node that we want to make prediction for, and so how that how that influences decays as we go further away from the target node. And so with that in mind, we can show that local subgraphs around target nodes contain all or most of the relevant information, meaning that if we focus on local subgraphs rather than in the structure of entire subgraphs, entire graphs, we can preserve near the same feature information. So intuitively, the way to think about the use of subgraphs is in the following manner. So mostly in graph machine learning, we think about two sources of predictive power in graphs. One source comes from label propagation, the idea that nodes with the same label will be nearby in the graph. They will be in vicinity of each other, and therefore propagating labels along edges of the graph will allow us to find and identify and annotate those nodes accurately. The other aspect is that of structural similarity, where the idea is that nodes with the same label, they would have similar structure or shapes in their respective local neighborhoods, but they don't need to be close to each other in the graph. And so if we take that into account, then in settings where labeled data are very limited and labels are scarce, it's easy to see that label propagation will not really be sufficient, because one cannot reliably and efficiently propagate labels there along edges of the graph, as there are so few of them. So we need to better leverage structural similarity in those settings, and that is exactly what local subgraphs can achieve. So just to summarize, GMeta is a few-shot learning approach for graphs. It uses local subgraphs to transfer information across different tasks, and can learn quickly how to adapt a new task using only a handful of labeled nodes or edges. And it's possible to show, and we show that in the paper, that the evidence for prediction can be found in the local subgraph around the target node or edge, further justifying the use of local subgraphs for few-shot learning on graphs. So I will not go much into technical details about GMeta, but I want to focus next on one specific use of few-shot learning in graphs for the problem of drug development. We have many other applications as well. I'm listing here another one in protein biology, where the goal was to annotate proteins across 2,000 different species, everything from humans to monkeys, zebrafishes, fish, mice, and so on. But I will not have the time to go into that. So let's just talk about how few-shot learning can really help us to accelerate drug development. So I will be very, very practical here. And so in settings where we need rapid therapeutic innovation are those settings where typically we need to very quickly find safe, effective drug for a disease that we don't understand well. In those settings, traditional iterative development, experimental clinical testing and approval of new drugs is not feasible. Why? Because it takes on average 12 to 16 years to develop a new drug from scratch. And it costs lots of money, but even if that is not an issue, it still takes 12 to 16 years to develop a new drug. Yet when we are in the phase of, in the time of pandemics, it's important to be able to develop a safe and effective drug very, very rapidly. We cannot wait 12 to 16 years. So the particular study I will outline today is a study that our group led computational efforts for, and it's about identifying drugs that will likely have therapeutic effects in COVID-19 patients. Why is this challenging? This is really an example of the frontier of science of medicine, as that disease have never been seen before 2019, and there are no labels or examples of drugs that were safe and effective for it. What I will outline is a study that we did between March 23rd last year and June 15 last year. So this is a span of 3 months of time where we were able to go from collecting data, training our graph neural network algorithms, generating predictions, and then biologists and virologists went to the lab with live virus and tested our predictions. So it's really an example of how years or months of time can be compressed to weeks or days in certain cases. And that was possible through the use of algorithms and automation, and the algorithms that were used were graph neural networks. Okay, so at the core of this question, the core of this problem was the question of identifying what drug can treat what disease. So essentially the way to think of it is our goal is to predict possible links between drug nodes and disease nodes, where those links would be indicative of successful, effective treatment relationship. We want to predict what diseases a particular given compound might treat. And we want to do that in the context of a lot of other biomedical knowledge and information that is out there about how proteins interact with each other, how drugs affect proteins by binding to them, and then those effects propagating to the underlying networks. But the key challenge is that we want the disease that we care about is COVID-19. And for COVID-19, there are no, in March 2020, at least there were no examples of treatments available. So it's really, how can we learn good classifier for drug nodes or be able to do a few shot link prediction for drugs in order to identify what drug would be potentially useful for COVID-19, but we don't have any example of successful drugs for that. The first question that emerged is, how can we even computationally represent COVID-19 disease? And so for that, we relied on data generated by Gordon et al. From UCSF. They were able to express 26 out of 29 SARS-CoV-2 proteins, and then use mass spectrometry, which is a type of biotechnological platform, to identify what are proteins in human body that the virus attacks. And so there were 332 proteins in human body that the viral proteins attacks. And those 332 proteins for us were computational representation of COVID-19 disease. So COVID-19 was a subgraph of the entire network of interactions between human proteins, and it was a subgraph induced on those proteins that the virus attacks. Our data set and experimental setup was then to construct a large COVID-19 repurposing knowledge graph that consisted of the reference human protein interaction network. This is a network where nodes are proteins, edges are physical links, interactions between proteins. We have information on all US approved drugs and proteins they bind to, and information about tens of thousands of different diseases, and of course also this COVID-19 disease module. The task was then, given this background knowledge in common diseases and treatments for common diseases, how can we predict candidate treatments for COVID-19 disease, which was that emerging, never before seen disease with no labels and no successful treatments for it. And so the idea here was to put to use our G-meta algorithm in such a way that we, during the meta training phase, we specified and trained G-meta model over a large number of training tasks. Each training task was formulated as a drug repurposing problem for a given disease. So in each task, we asked G-meta model to try to use very limited number of drugs and predict what are drugs that would treat one disease number one, for which lots of data are available and it's well-characterized disease. And then another training task, number two, would be a training task about predicting what drugs might work for another disease. And we had many, many tasks like that, so that at the meta testing phase, the model was instantiated in the zero-shot learning setting, where it was required to make predictions for COVID-19 and produce a prioritized ranked list of drugs based on how likely those drugs would be effective for COVID-19. And the first thing we did to try to make sense out of that list of predictions is we took a predicted list of drugs, and where at the top of that list were drugs that, according to the GNN model, they were most promising opportunities for COVID-19. We compared that list against the set of drugs that were in clinical trials back in March 2020. And that was information that we used to calculate performance metrics. I'm showing just one example here on the left, showing how GNN methods performed in terms of a ROC metric here substantially better than a variety of more classic drug repurposing and network-based strategies. That has motivated us to really use those predicted list of drugs and inform experimental screening of those drugs. And so we teamed up with collaborators from National Emerging Infectious Diseases Laboratories. This is the US government laboratory that is credited with ability to test drugs and how they affect human cells that are infected with the virus. So what they did for us, they took our ranked list of drugs and then they ran experiments in that lab by designing cultures of cells where they put in those cells first African monkey cells that were infected with the virus and the drugs that our model predicted. And then they measured whether those cells still survive after some time in the presence of the drug. And if the cells survive, that's great, that's a win. For us, that's a positive prediction. If cells die, then that means that the drug didn't do anything good to them. So virologists have tested 918 compounds for their efficacy against the virus, first in monkey cells, then in human cells. The results of that was that by screening top-ranked drugs in human cells, we obtain a near 62% success rate. In contrast, one would get only 0.8% success rate or hit rate, in this case measured as hit rate, if screening would not be guided by our algorithms. And so that's exciting because it clearly shows what is the use and utility of these algorithms in real-world practice for biomedical discovery. It's an order of magnitude better hit rate, looking at top 100 drugs than what would be possible by alternative approaches. And that also allowed to compress the timeline very effectively. We were wondering, well, is there anything common to those drugs that our models have predicted and were also successfully validated and confirmed through experiments on human and monkey cells? And that in order to explore those drugs, we use our GNN explainer and a few other explainability algorithms. And it turned out that out of 77 drugs that the model has successfully predicted and correctly predicted, 76 were such that they reduced viral infection by not binding to proteins that the virus attacks, but binding to some other proteins that indirectly interact with the proteins that the virus attacks. Why am I mentioning this at this particular venue? I'm mentioning this here because that led to the discovery of a new class of drugs that we now call network drugs, because the way these drugs work is they work by treating the disease not directly targeting the disease, but targeting some other proteins, and then those proteins in turn interact with the disease. And the way this discovery was facilitated, it was facilitated first by very accurate predictions produced by GNN models, and then the use of GNN explainers to try to find what are the explanatory subgraphs that the model has used to make the prediction, and what is common to those explanatory subgraphs when we look at drugs that actually were successful in their work. Okay, so what is next? Some of the exciting work that we are currently engaged in relates to diagnosis of patients in addition to predicting safe and effective treatment. And why that is important, because the classical and way of doing it in medicine is to adopt a one-size-fits-all approach, which, as you can imagine, does not work well. So we're now teaming up with the Undiagnosed Diseases Network, which is a nationwide network in the US, in order to really design these actionable graph neural network frameworks that allow domain experts to interact with our GNNs, ask questions, and then get predictions that can be interpreted in a very meaningful way, and also tailor treatments for the patient level rather than at just the level of populations of patients. So I will talk perhaps more about that some other occasion. But to wrap up today's talk, there is one important highlight that I would like to make. And so perhaps some of you became interested or excited about applications and the opportunities that drug development, more broadly, therapeutics offer for graph machine learning. And so if that's the case, a natural question to ask is, well, how can we advance machine learning for therapeutics, and how can one start? Where should we start? And so here what I'd like to share is that over the last year or so, we've been working on an initiative that is known as Therapeutics Data Commons Initiative, and it's a collection of AI-ready data sets and machine learning tasks for therapeutics. The website is up, it's tdcommons.ai, and it's meant to serve as a meeting point between domain scientists who identify meaningful tasks and data sets, and then machine learning scientists who design powerful machine learning models. And over the few months that TDC is out, we have already seen around over 20,000 active users using data sets and machine learning tests together with strategies for model evaluation and metrics in TDC. And of course, I want to kind of highlight all the inspiration that we got for TDC from the work that the OGB team did, and Wei Hua in particular, who is also here on the call, I believe. So Therapeutics Data Commons is the first unifying framework that allows us to systematically access and evaluate machine learning across the entire range of therapeutics tasks beyond just drug discovery and repurposing that I mentioned today as one application. It currently includes over 66 ML-ready data sets. They span 22 learning tasks that go from predicting individual labels of individual entities, sets of entities, modeling and generative tasks. It also comes with an ecosystem of tools and libraries, public leaderboards, and community resources. So it really can support the entire life cycle of therapeutics machine learning research with a variety of data split functions, molecule generation oracles, processing helpers, visualizers, and so on. To kind of highlight here is that TDC creates exciting new opportunities for graph machine learning community. I'm sure that many have noticed that the questions related to drug discovery have become quite an exciting topic for graph machine learning community, but current efforts have been primarily focused on one type of drugs that are small molecules. There are, however, many other opportunities that would also benefit tremendously from advances in graph representation learning. So I hope that with TDC, we will be able to kind of also highlight and encourage the graph representation learning community to also focus on other important opportunities that are in this space beyond embedding molecular graphs. And so one of that is certainly that are certainly questions related to graphs that come with lots of textual data that would, in our case, be various sequences, information about proteins and genes. And so those would be text-intensive graphs, as well as image-intensive graphs, where you can think of graphs that are supplemented by images of cells that are infected or healthy, or and also graphs that are knowledge intensive and have lots of additional background knowledge information available that one could leverage for prediction. It's an open science initiative. We very much welcome contributions and would be excited if you try it out and let us know your feedback. So I'll wrap up here. Papers, code, and data for all of the projects that I've been mentioning today are available at our lab website, zitninglab.hms.harvard.edu, and I'm happy to take questions in the remaining time I have.
Yeah, thanks, Marinka. It's really a great encouragement to see the progress on graph machine learning for COVID-19 drug repurposing. Yeah, it's really exciting. Okay, any questions from panelists? Please go ahead. For attendees, please post your question in Q&A. Yeah, thanks.
Yes, I have a quick question, clarification question. Hi, Marinka. Great talk. Thank you very much. So I'm interested in like this question of predicting the drugs that treat disease, and you formulate it as a future learning problem, which means that you kind of need to know the few drugs that actually treat the disease. But for COVID case, we probably don't know any drugs that treat the disease. And how would you like go with this kind of issue?
Yeah, so in the COVID case, the test became a zero-shot learning test. So we didn't have any examples of successful treatment. So the only data we could rely on was the data about other common diseases. So we put in lots of efforts to get information for around 20,000 diseases that are well studied and for which treatments are available. And so then the modeling, the way it was, is to essentially pre-train or design these training tasks around those other diseases, right? For each of those 20K disease, specify a few short learning tasks that would allow us to learn good subgraph signature functions. Once we do that, then we transfer those subgraph signature functions to COVID-19 and produce a ranked list for drugs for COVID-19.
I see. So for COVID, we don't need any drugs like
yes, exactly. No successful example of treatments that and by now there is quite some information available and known, but when we did that in March 2020, where really very little information was available. So the only data given to the model about COVID-19 was this subgraph of 332 human proteins that COVID affects.
I see. Thank you very much.
Any questions, Xiong?
Marinka, yeah, very nice talk. I hope this is again a request for comment about this data commons. So this is what we are looking into now. So I really want to know is, so this is a really nice bridge between the methodology, machine learning people, and the real application, the therapeutic field. So I want to know, like, what is your thought about how these problems are close to the real world problem. So I know that you have been working with all the hospitals to solve real problem, and you abstracted this problem out. So suppose we are able to solve some of these problems, how close are we going to solve the real problem for, let's say, for really for hospitals, for medicine?
Oh, so wow, that's a great question. So So I would say there are two types of data sets in TDC Commons. One type are data sets that are focused more on biological discovery or early stages of drug discovery and development that are far away from patients. They are those questions related to identifying candidate compounds that have specific desirable properties that are required of any drug. And so those questions are very close to practical use, not by hospital, but practical use in by pharmaceutical industry. And we have a large number of collaborations with some of the big pharma companies who are using TDC, and we work with them to transfer some of the models for tasks around proteins, around compounds to their practical internal pipelines. So those tasks are very close to practical use in discovery pipelines in industry. The other type of tasks are tasks and data sets that would relate to modeling patients and prescribing drugs to patients and trying to figure out whether the prescribed drug will be safe or not. We have some data sets available for those questions in TDC. There are data sets that you can, that are, I think most exciting are those that are about predicting response of patients to drugs that treat cancer. And that data, that is further away from clinical implementation. And the reason for that is that to kind of move closer to clinical implementation, one would need to really use patient level information. But that data, of course, we cannot share through therapeutics data commons because of the privacy and security concerns. We will have, however, very soon, probably early next year, a public competition with that will be sponsored by a company that has a large number of clinical trials that will make some of their data available to TDC and the use of for a competition there. So that will be very realistic of clinical trial design.
Oh, that's wonderful. That's really exciting. We really look forward to the challenge. Thank you, Marika.
Thank you.
Thanks again, Marika. I believe we don't have too much time for the Q&A. Yeah, thank you very much for the great talk. And Larry, can you go ahead to share the screen? Hi, Larry. Yeah, cool, thanks. Yeah, so it's my great honor to introduce our next keynote speaker, Dr. Larry Zitnik. So Larry is a research scientist at Facebook AI Research. Previously, he was at Microsoft Research, and he got his PhD from CMU's Robotics Institute. His research includes artificial intelligence, language and vision, creativity, object recognition, as well as scientific applications. So Larry led a few very impactful open datasets and benchmarks, including the Microsoft COCO dataset for object detection and the VQA dataset for visual question and answering. So I believe today Larry is going to introduce how to create impactful dataset and benchmark, as well as introducing the Open Catalyst project. So without further ado, Larry, please go ahead. Yeah, thanks.
Thanks for inviting me. I'm happy to be here today. Even more excited to follow another Zitnik in a presentation. I don't think that happens. It's probably the first time in my career this has ever happened. It's also just cool to see all the different applications that GNNs can be applied to, the real world applications that people can take the research and hopefully have an impact. And I'm hoping my talk today basically highlights another one of these applications with the Open Catalyst project. So I just want to recognize, starting off, that what I'm presenting today is the effort of a large team, both within FAIR and CMU. Wei Hao was helping us out at one point as well, and then we have some folks from NERSC as well working on this project. So one thing that I know is top of mind for many of us, and a top concern, is climate change. And when you look at the energy production in the US right now, the majority of it is still being done with natural gas and coal. And if we are going to have an impact on climate change, we need to change this. We need to figure out a way to have more renewable energy in our energy grid. Now, what you might think is, okay, all we need to do is, go and build, more wind turbines, more, solar panels, and voila, the problem could be solved. And if you look at this is just an average day in California. I think this was in August, and you can look at the demand, which is in the blue line, and you can look at the amount of energy generated by wind and solar in the green. Now, if you think to yourself, okay, what if California just increased the amount of solar and wind by, let's say, 3x? What would happen? You'd get this. So hopefully what you see is immediately two big problems. One is that at noon, when the sun is shining, we're generating too much power. So we have excess generation. And at the flip side, at night, and we're in the evening, let's say around 6 o'clock or 7 o'clock, when the demand is spiking, we actually have an excess demand because the sun's no longer shining and all we have is wind power and we can't meet demand. So basically, we have this problem where we got to take this excess generated power that happens during the day, we got to figure out how to store it so that way we can use it at night when demand peaks. And this isn't just a daily thing. You can think of this as seasonal too. If you live in Seattle, there's a lot more sun in the summertime and not much sun in the wintertime. So as you go up, and then obviously the wind fluctuates too from week to week. So one question you might ask yourself then is, how do we actually store renewable energy? How should we be, how are we going to do this? And if you ask people, basically two main ideas kind of pop into people's head immediately. The first is batteries. Batteries are good. They're good for short-term storage, but they unfortunately just don't scale well to nation-sized grids. They work for good, smaller installations, but when you start thinking about, okay, how do we actually build enough batteries for the entire of like the US or Europe or the world, this is going to be really tough. The second approach is pumping water uphill. Now, this is a brilliant solution. All you do is when you have excess power, you take water and you just pump it up into a lake, which is like higher up. And then when you need power, you just use a hydroelectric dam to generate electricity. And this is fantastic. It works great. It's super efficient. The problem is there's only like so many mountain valleys that you can flood before you run out of space. And we just like literally just don't have enough space to store the water for the amount of energy that we use and we need. All right. So a whole nother different solution is to use renewable energy to create new forms of fuels. So what you could do is you could take electricity, generated through renewable energy, to split water into hydrogen and oxygen. You then store that hydrogen, storage is cheap, and then later you can use that hydrogen in a fuel cell to then generate electricity. Another thing you could do is you could take that same hydrogen, you could combine it with CO2 from the air or a smokestack, and that'll create methane, which is essentially natural gas. And then when you need electricity, you just burn it and hopefully capture the CO2, and then you can generate electricity that way. And what's nice is in both these examples is you can do large-scale storage of hydrogen or methane or ethanol or other fuels that you might want to generate, and it scales really well to nation-sized grids. So so you might think, okay, well, actually, but the problem here, though, is that we need to figure out efficient ways of generating the hydrogen and then generating methane, and then also using the hydrogen to generate electricity. And I'll get to that in a little bit. And these are all chemical processes. And believe it or not, if this were to work, something like this were to work, this isn't the first time that chemists have come to the rescue for the world. So in the late 1800s, there was a real widespread concern that the world was going to run out of food because the fertilizer we were using came from just a few islands in the world, basically bird poo. And that fertilizer was running low. People didn't know what they were going to replace it to. The population of the world was exploding, and everybody was really worried about how we're going to get fertilizer. And it was a couple chemists that figured out a process to get nitrogen from the air to create ammonia to then generate the fertilizer. And that is what has supported the population of the planet to this point. So hopefully we can do the same thing here. So what's critical when you think about chemical processes is you want to make them efficient. And what really drives a lot of these chemical reactions is something called a catalyst. And a catalyst is a material used to increase the rate of a chemical reaction without being consumed in the process. So let me just give you an illustration for how a catalyst might work. So let's take a really simple reaction here where you have two water molecules, and what you want to do is split those water molecules to create an oxygen molecule and some hydrogen. So this is going to be a little video. What we have is the catalyst in the bottom there. A water molecule comes down. It interacts with the catalyst. It bonds with the oxygen, bonds with the platinum, which weakens bonds with the hydrogen, and the hydrogens go fly away. Another water molecule comes in. Same thing happens to it. Its hydrogens fly away as the oxygen bonds with the platinum and the catalyst. And then those two oxygen atoms basically slowly kind of move together. And when they get close enough to each other, they form a really strong bond and they float away from the catalyst. All right. So this is essentially an illustrative example of how a catalyst might work. Now, what's interesting here is you have to make sure that bond that oxygen has with the catalyst is just right. If it's too strong, like if you had iron as your catalyst, the oxygen would basically bond with that iron and never let go. And then eventually the entire surface would be covered with oxygen, and this is basically called rust, and the reaction would stop. Let's say you have a catalyst like gold, the bond isn't strong enough, and the water molecules never interact, and basically nothing happens the same way. So what you need is the catalyst, which is just right. It doesn't bind too strongly, but it doesn't, but it binds strongly enough. And the unfortunate thing right now is that the best catalysts that we have, most of all of them use platinum or similar metals, which are really expensive. So the trick is, can we find catalysts that are just as effective, but much less expensive? All right. So how do people actually go about testing and finding new catalysts? Well, what they do is they find something called the relaxed energy, which is essentially a measure of how strongly attracted the absorbate, which is the water molecule in our previous example, but it's basically the molecule in the chemical reaction binds to the catalyst. So here you see we have an absorbate here and we have a catalyst. And the way that you typically compute the relaxed energy is use something called density functional theory, or DFT. And what DFT can give you is the forces on each atom. So it's how much do each of the atoms impact each other and how much are they pushing each other in various different directions, and then the overall energy of the system. And if you can use DFT, what you can do is you can do something called a relaxation, which means you can place a molecule near a surface, and this is this molecule here, and then basically you compute the forces, and then given those forces, you update the atom positions, and then you re-estimate the atom forces, you update the atom positions, and basically repeat until you get to a local minima. And you can see here, it kind of looks like it kind of gets kind of snugged in there, and that's basically a local minima. And once you find that local minima in the energy landscape, that is your relaxed energy. You can use that to help estimate your reaction rate. So that would be fantastic. That'd be awesome. We would just scale it up and we'd be done. Except for one fact, which is each of these relaxations takes about 8 hours of compute. And that is a lot of compute. And the problem is it's not like we're just testing out 10 different catalysts, or we're just running a small number of simulations. We need to be able to run tens, hundreds of millions, even billions of possible simulations. And if each one takes 8 hours, computationally this is just infeasible, which is one reason why progress in this space has been quite difficult. So that's one of the things that we want to help address. And and to help raise awareness to the space, what we're doing is we're going to be hoping the Open Catalyst Challenge at NeurIPS this year. I was super excited to see so many entries in the quantum chemistry included in the KDD Cup this year. I was actually really curious that the top 3 entries were super close in accuracy. So it's great to see a lot of competition in the space and a lot of great approaches being developed for this task. And for the challenge that we're going to be hosting at NeurIPS this year, what we want to do is we basically have a task where we're going to give the initial structure, like I just demonstrated, and we want the algorithms to predict the relaxed energy. So basically, you have an initial structure like the 3 examples you see here. The relaxed structures look like these here, and what we want to know is what the energy is of those relaxed structures given the initial structure. Now, there's a couple different ways of approaching this problem. One is kind of conceptually the simplest, which is we call it direct method, which is basically you just take the initial structure, you model that usually with a GNN. GNNs are super popular for this task. And then you just spit out the energy. It's a single value. So fairly simple. The other way you can do it is what we call the relaxation approach, which is you have your initial structure, you have a model, but instead of predicting energy, it predicts the forces per atom, and then use those forces to update the atom positions. And you keep iterating that just like you would with density functional theory, DFT, you do your relaxation, define your relaxed structure, and then given the relaxed structure, then you compute the energy. And the theory is that computing the energy from the relaxed structure will be a lot simpler for the algorithm than computing the energy from the initial structure. And I'll show in a little bit how the accuracies differ for the 2 different approaches. All right. So let's first talk a little bit about how to apply ML to this problem. And again, what we're trying to do here is we're trying to take a process that takes 8 hours to do, and we're hoping to get it down to approximately a second, about 10,000 times faster. So that way we can really scale these methods. So generally, we're going to be using a graph neural network where each node is an atom. Each edge basically represents the neighbors of the atoms. And then the inputs are the 3D atom positions and their atomic numbers, whether they're carbon, oxygen, et cetera. And then the output is simply the energy of the entire system or each individual atom's forces. In X, Y, Z, it's a 3-dimensional vector, which is the force in 3 dimensions. Now, you would think this problem wouldn't be too tough because you look at 2 atoms and you say, how do they interact with each other? Basically, you can have when atoms are far apart, they basically slowly attract each other. When they're too close together, they start repelling each other. So it's a fairly simple graph, as you can see here, with the basically repulsive and attractive forces with just 2 atoms. The problem, though, is when you have many atoms, is forces get really sensitive to very small changes in positions, changes in angle, because it's not just, an atom is not just a single point in space. It's actually electrons flying all over it. And the electrons they're very odd creatures. They do like, I mean, they have all these, you know, bizarre orbitals, and they're very complex. So you can imagine like, it's like, yeah, the simple kind of nucleus of an atom, but then you have these electrons doing very complex things, which then impact the overall interaction of the atoms themselves. And to model that is really hard. And to do it, you know, successfully, I think we need a lot of training data to do this. And this is one of the first things that we started tackling with the Open Catalyst project, was generating large data sets. So we generated 1.3 million relaxations for training and evaluation. This took about 70 million hours to compute. It's basically 3 months of time on 50,000 Facebook servers. And this data set ran out. It's open source, it's out there, you guys can use it. And it's out there for everybody to use. Now, for the NeurIPS challenge, basically, you can use one of two data sets. One is the IS-RE data set, which basically has about 460,000 initial structures, and then with corresponding relaxed energy. And then we have another data set, which we call S2EF, which has 130 million structures, which have corresponding forces and energies associated with them. So it's a lot bigger training data set for if you want to do the relaxation approach. And why is there much more training data for the relaxation approach? The answer is simple, is when you perform a relaxation, there's actually, you have that iterative process, right? So when you have an initial state, you have basically 200 steps on average to get to the relaxed state. So for every one of your, initial structures to relaxed energy, as part of that computation, you actually generated 200 additional training examples, which is what's provided in the relaxation approach. All right, let's talk a little bit about models and different approaches you can take. So again, inputs and outputs, 3D atom positions and atomic numbers are the input, output are the 3D atom forces and energy. There's basically two kind of general approaches. One is energy centric, which means that the output of the neural network is just the energy. And then you find the forces by doing a back propagation, essentially, to take the negative gradients of the energy with respect to the atom positions. And the other approach is a force centric approach, which you output both the energy and the 3D atom forces. So if we look at the energy-centric approach, basically the 3D positions and the atomic numbers are set as input. You feed it through your model, you compute the energy, and then you do a backwards pass to then estimate the 3D forces. And what's nice about this is the neural network, essentially all it's computing is this kind of energy, surface here. And it has this property where it'll conserve, the forces are conservative. So basically what that means is you can go from point A to point B to point C and back to point A, and if you sum of the forces along that path, they should all sum to 0. So this is a nice property that the energy and the forces that you estimate are consistent with each other. So just to give you like a really simple model, Chinet is one of the earlier models trained for this task. And basically what you would have is the output of the neural network is going to be your energy E. You sum over all the atoms, you have some neural network F, and then you have an atom hidden state for every atom. You have a hidden state H here, and then that hidden state is refined over K iterations. So it's kind of your standard kind of graph neural network approach. And then you have your graph such as this, and then your hidden states are updated by summing up the messages into that node. And then this is basically the message update. It's fairly simple. There's a bunch of other approaches that have improved upon this since then. But one thing you want to note here is you have this edge information coming in, which is basically telling you what the distances between the atoms, and you use that to basically update the hidden state of the atoms. And if you look at the filters that the Chinet learns, you can see, and these are basically based upon the atom distance, you learn kind of all sorts of interesting and kind of cool looking filters here. Now, one of the problems with Chinet was it didn't take into account the angular information between atoms. It just measured how far away they were. But if you want to measure the angular information, this is a little bit more complex. And one of the big challenges that we have right now in the field, which is how do you efficiently model the angular information? And the way that DynMet did that is it looked at sets of 3 atoms, and then it would look at the one angle between the 2 atoms. And it would represent the atoms using basis or spherical harmonic functions. And you can see some of the learned filters here. Again, pretty cool looking. The problem was you had to model this for every triplet of atoms. So since you're modeling every triplet of atoms to model these angles, then it was basically order n cubed with a number of atoms. So computationally, it's a bit more expensive than like the Chinet model. And the model itself was a bit more complex. Again, we'll go into this, but just to give you guys an idea of the complexity of this. And again, there's been a couple models after this called like GemNet by the same authors, which have been improving upon this. So the force-centric approaches Basically, you take the 3D atom positions in, you have the model, and then you just spit out directly the 3D forces and energy. And this is just a regular forward pass. It's not energy conserving like the previous one, which basically means the energy and the forces may not be consistent, and then generally they aren't, approximately so, but not exactly like in the previous energy-centric approaches. But the positive you get is generally they're a lot more efficient because you don't have to do the backwards pass. And in many cases, they're actually more accurate as well. There's a bunch of force-centric approaches out there. I won't go into them today because I just don't have time. But SpinConf was a new model that we just put out. Beha and us released ForceNet a while ago, and then GemNet. We've seen some good results with this. So if you guys are interested in this space, I would check out the GemNet paper as well. The Noisy Nodes paper, which did well in the competition here, also did really well and does well on OC20 as well. And one of the big questions is how do you model this angular information? And SpinConf has an interesting way of modeling the angular information of sets of atoms, in case you want to check that out. All right, so let's look at results real quick. So basically, take home here is that a lot of these models are fairly complex or take a lot of time to train. They've been trained on 32 or 64 GPUs. It can take many days to do that. And this is being trained on the S2EF, the 130 million data set. So computationally, these can be a bit expensive to train. One thing we did do in generating the OC20 dataset is we generated 4 different test splits. One which was in domain, which is basically the same distribution as the training dataset, but then we have 3 different out of domain sets. We wanted to see how well these algorithms generalize, because we don't want these algorithms just to interpolate in between what they saw, but we want them to generalize to new absorbates and new catalyst materials. Now, if we look at the actual results, what you'll see is for the direct approaches here, you can see, steady progress. Noisy Nodes, again, which did well in the competition here, is the best direct method that we've seen so far. And you can see it does better in the in-domain. It doesn't do quite as good on the out-of-domain task, but that's kind of expected. If we look at the relaxation approaches, generally, the relaxation approaches do better. Again, computationally, a little bit more expensive because they actually perform a relaxation and then they compute the energy. And the accuracies are much higher. And they seem to generalize a little bit better across the outer domain as well. So that's nice to see. Now, one question you might ask is like, okay, the numbers are going down, but when are you good enough? And talking to the experimentalist and the computationalist, the chemist that we collaborate with, we can get it down to 0.2 EVs, so basically reduce the error by by 50% or more. Then we probably it'll start hopefully being practically useful at that point. And just to give you like an illustration of what an ML relaxation looks like, this is one that the SpinConf model produced. So you can see it kind of starts off and then it finds an energy minimum, which is a little bit farther away. It's kind of cool looking, I know. All right. And then just to wrap up going forward, if you are interested in working on this space, my background's in computer vision. I've worked in a lot of different areas, but I found this problem super interesting. The combination of chemistry, the complexity of the problem, and like trying to think of new ML algorithms to solve this has been super interesting over the last year or two. If you want to check it out, go to the opencatalyst.org. There's papers, code, leaderboard, discussion board, everything's there. We have the code base. It should hopefully be easy. It's in PyTorch to get you up and going. There's already models. There's scripts and training. It should hopefully be easy to get yourself up and going on it. And then we have the NeurIPS challenge coming up. So we're going to release the challenge test set for you to run your models on. It's September 20th. We're giving everybody 2 weeks then to run their models and upload the results. And then at NeurIPS this winter, we do the winners announcements and presentations at NeurIPS. That's all I have for you guys today. And again, if you want any more information, go check out opencatalyst.org. And there's a couple papers there for more background on this topic. Thank you.
Yeah, thanks, Larry, for the great talk. Yeah, very new perspective, at least for myself. So yeah, any questions, please?
Okay, Larry, very nice talk. So I want to know, you had talked about this direct and a two-step approach. So for the two-step approach, I think my question is, so given the initial structure, And will this relaxed structure be unique? Of course, in your data set, I think it's unique, but computationally, if I run this for the second time, will I get the same relaxed structure?
If you run DFT twice on the same initial structure, you'll get the same result up to numerical precision. However, if you run, let's say, 2 different variants of DFT, and there's several different variants of DFT and approximations that, because DFT is an approximate method as well, and people use different approximations for it, you might get slightly different answers. And this is particularly true, let's say, if you have like 2 atoms here and another atom here, and either this one's going to go here, it's going to go here, and just like a little bit of numerical precision one way or the other is going to pull it here or there. So, it's not going to be, perfectly, so you could get slightly different answers in those cases. But yes, I think for, from an ML perspective, you can kind of assume it's going to be deterministic.
Yeah, so, but in your data, you use the one particular fixed DFT method. So
yeah, so we have a lot of different evaluation metrics. One thing that one of our evaluation metrics is we want to know if you perform a machine learned relaxation is whether you actually found a true energy minima. And there's 2 ways you can do that. One is to say, are the atom positions close to the atom positions that the DFT, the ground truth, relaxation found, right? And if the atom positions are close, then you found it. But for the exact reason that you're mentioning, that's not perfect, because maybe you found a different local minima, that's equally good, because you have a lot of symmetrical local minima. So another way to do it, and this is one thing that our leaderboard supports, is that it'll actually perform a DFT calculation on your local minima and see if the forces are equal to 0 there or close to 0. And if the forces are close to 0, that basically implies that you're at a local minima. So that's the way that we've been evaluating this problem, is both by looking at the distances, but then also doing basically a single point DFT calculation on a machine learning relaxed state to see if you actually truly found something where the forces are all close to 0.
Okay, that's great, because if the relaxed state is not deterministic, so you can imagine that the neural network might be confused because the rules seem somehow some kind of there's some kind of randomness there.
Yeah, and I think it's not as big of an issue when you have like the small absorbates, a small molecule, so like with 2 atoms or 3 atoms. But we have some absorbates which are pretty large, and they can have like 12 atoms or something in there, and they go through really complex like distortions and that sort of thing. And there, I think your point's really valid, because there could be a lot of really close local minima, and you just want to make sure that you found one of them.
Right. Okay. Thank you, Larry.
Any other questions?
Yeah, so I have a question. So I was wondering if you have, or you can share some intuition on what is currently missing in graph machine learning models in order to achieve better performance on this task. Like, is there still some open research questions on the model side?
Yeah, there's a lot of open questions on the model side on this. So what has really impressed me is like what I was mentioning before, just the subtle differences in the distances between the atoms, like very small changes in distances between the atoms, and also the angular changes within the atoms can have big differences and big effects on the forces. So the question is how do you model these subtle differences in a way that doesn't computationally get too expensive? So if you think about the angular information, if you just model every set of 3, then that model that grows n cubed. But then let's say you don't want just like the angular information between like say 3 atoms, but you want an atom and the angular information with all the atoms around it. It's like, what representation do you use to model all of the angular information that can like model these higher order interactions between all these atoms that doesn't grow, into the 4th and into the 5th, into the 6th as you get, higher and higher order interactions. And then, the systems that we're modeling here as well have, maybe 100 atoms in them. So they're large, but not too large. But if you go to experimentalists and you say, what's going to come next? If the models start getting accurate, you want it to be able to scale not just to hundreds, but to thousands or tens of thousands or millions of atoms to make it more and more realistic to model what's going on experimentally. So I think that's another challenge. And then finally, DFT is approximate itself. So, I think we're using DFT here just to see if we can do it. But then I think at the end of the day, we're going to have to improve DFT as well to make these, computational simulations accurate enough to then predict what we see experimentally.
Okay, thank you. So a follow-up question I have is like you showed that table showing the training times of all the models, and there were like 200 days and 300 days and stuff like that. So how important is training time on this task in comparison to just like pure model performance?
Yeah, one note on that: if you have like 30 GPUs, you can cut that down by a factor of 30, right?
Okay, so that is a single GPU runtime.
Yeah, single GPU day. So so not as bad as it looks. So generally, we're training our models for like 3 days to a week, depending on the model type and that sort of thing. It is important to train it for a while. I haven't seen many. I mean, you do occasionally get that crossover effect where something converges really quickly and then plateaus earlier, and you have another method which like does poorly at the beginning and then it gets better later on, which can make it difficult because you really have to let it train then for 3 to 4 days to see if it's going to work well or not. But some of the new models that we've seen, like GemNet, can train much faster. DimeNet++ does much better than DimeNet. So we're seeing an improvement in the efficiency of these methods, which is great as well. And then if you train for the IS to RS or IS to RE task direct, if you use the direct approach, essentially, that can train a lot faster because the training data set's only 500K or 460K versus 130 million. So that's like a good and then even on the 130 million data set, we have a 2 million split and a 10 million or 20 million split. So I would recommend kind of like prototyping your approaches on like the 2 million split, because I found that if it works well on that, it generalizes well to the entire data set then. And that can basically increase your the rate at which you can test new ideas.
Okay, thank you.
Yep.
Yeah, thanks again, Larry, for the exciting talks and the inspiring discussion. So I believe this will include our keynote session. So our panel session will start in, I believe, 20 minutes. So please come back in 20 minutes for the panel session. We have an exciting lineup of panelists from different org, including some winners of the KDD Cup on this task. Yeah. So please do come back in 20 minutes. Yeah. Thanks, Aaron, again for attending the keynote session.
Okay, see you soon.
Zhang's research interests are theories and practices of large-scale distributed computing and its intersection with machine learning, particularly deep learning. He's leading the Deep Graph Library, a popular library for graph neural networks. Next, Dr. Suiwon Ji is an associate professor at Texas A&M University. His research interests are machine learning and data mining, and his recent research is focusing on GNN for molecules and other scientific discovery applications. He received National Science Foundation Career Award and is a distinguished member of ACM. Finally, we have Dr. Jen Tan. Dr. Jen Tan is associate professor, assistant professor at Mila. His research interest is graph representation learning, graph neural networks, knowledge graph, drug discovery, and recommender system. He received the Best Paper Award at ICML 2014 and developed a well-known early node embedding methods called LINE. This conclude my introduction to all the speakers. And now let's jump in to the panel discussion. And for the audience, please type in any questions that you're curious to ask on the chat. So let me first start with the topic. So far in the past few years, many works have been done in graph neural networks. Like the most increasing keyword in IQ conference for the last few years is graph neural networks. And many architecture have been proposed, many scalable sampling techniques, and many self-supervised techniques have been proposed. And I want to hear everyone's thoughts on what remains the biggest open challenge in machine learning and graph. what's the biggest unsolved problem, that hasn't been solved over the past few years despite a lot of work. So that's the first topic to discuss. Anyone have any thoughts? Please go ahead and talk about your thoughts. Thanks.
I can start.
Yes, go ahead.
So I think for the graph domain, right? So right now people have done lots of things. If we think in this way, it's more like forward path, meaning that giving a graph and we want to do lots of like inference on top of it, right? For example, through the representation learning, then we can know how we can do the node classification or link prediction or like graph level tasks. But the reverse way, I think it's more challenging, meaning that suppose we have a task in mind, it can be formalized as a graph problem. So given a graph, we can know how to evaluate whether, for example, the performance of that chemical compound is good or not, or whether like hardware architecture is good or not, or like whether a software program is good or not. But it's very difficult for us to do the reverse design. It's like we have a goal in our mind, and we know that how we can evaluate a graph, but how we can find the graph or how we can synthesize that graph. So like for me, I think it's one of the most challenging part. Yeah, so how we can do the reverse part of the graph synthesis. So should I just mention one? I could mention multiple.
Yes.
Or maybe just the one, because I will still have other panelists. Yeah. Okay.
Yeah, thank you. Thank you very much. Any other thoughts from other panelists?
Maybe I can also mention one. So I was actually impressed by one of the winning solutions in this year's like KDD Cup. So I think one of the team from DeepMind, so they are successfully able to train very deep graph neural network, right? So before I think it's actually very difficult to train a very deep graph neural network because of the problem of over smoothing. But this year I think they use some kind of technique of basically add another loss function on top of the supervised loss function. I think they add some like sort of like denoise autoencoder on top of the supervised loss function. So by doing that, they're able to train really deep graph neural network. I think this is actually very impressive for me.
Right. Yeah, that like yesterday there was a talk from DeepMind, and the trick was quite interesting. Yeah. It's basically like they add this auxiliary law so that the last layer of graph neural network still remembers the input. Otherwise, the over smoothing effect is kind of over smooth the information, but they add this additional loss to remember the input.
Yes.
So when you talk about deep graph neural networks, do you mean like training deep GNNs in molecular graphs, or do you mean like extracting long-range dependencies in a node classification problem?
I think in general, I think I would refer to learning molecule repetition. So basic graph level task. I think in general, I feel like for node level task, I think deep gen is not like it's not necessary, because if you really like try to apply a very deep gen to a node classification task, right? Because if you have very deep gen, then basically your neural network is gonna propagate many times, right? And then that basically for every node you're gonna reach every node on the entire network, right? So that means basically I think like when you try to learn the repetition for that node, you're also gonna like incorporate a lot of noise, right? Because think about like even like in social network, like the diameter of a network is just 6, right? If you have like a graph which is more than 6 layers, and basically for every node you can reach to any node on the graph, I think that's definitely gonna introduce a lot of noise. I think I think for deep gen, I think that's more there's more potential for graph level tasks like molecular property prediction. But for node level task, I think deep gen in gen I feel it's not necessary.
That's a great point. Yes.
Okay, great. I think yeah, I can try to go next. So I think what Yizhuo and Jia mentioned both quite challenging for me. I think what Yizhuo mentioned is how to generate graphs. I think Jia has done quite a bit of work in that way. I think it's still in terms of this area, I think it's still in early stages. For example, if we generate molecular graphs right now, so the results are quite similar to this. Not, I think, not similar, but not better than the tools that these chemists generate, like the RD kit. I think that there is still a long way to go. And for the prediction, I think actually that I'm quite in agreement with what Jia mentioned. So currently, if you look at, I think if you look at the path of development, we first deep learning first came from speech and images, and then to text. And what we have observed in past is for example, our images. I did imagery or deep learning like in about 12 years ago. So at that time, all these deep learning or images, the reason why there was very little research is, if you do deep learning convolutional network or images, your performance will be lower than all of these handcrafted features like SIFT, spatial pyramid matching, etc. So, and at that time, we believe that deep learning just did not work, just because deep learning is not suitable for images. But I think later people prove that if you have more data and if you can train deeper models, it actually worked. I think, and a similar thing has been going on for text, for NLP, and in recent years, we all know the BERT, GPT, etc. So I'm wondering, like, but I don't see that graphs right now. So I'm wondering, like, in some days, so if we are able, and we have a larger data set now through OGB and other benchmarks. So if we collect more and more data and we have more computing power, someday are we able to train a much deeper network and a more powerful one? And if we are able to do that, can we just similar to text and images, can we transfer this model to a domain where we have a very small data set? Because I worked with domain scientists, and many of them in chemistry, in chemical engineer, in biology, many of them need to predict, for example, property of molecule, but they don't have a large data. So they usually did experiment, or they make created papers in the domain. They only have like 200 molecules, and they want to make predictions. And I think if I don't think it's possible that we can train pre-train a graph neural network, and this model can be applied to transfer to many domains, like to molecular graphs, to social networks. I don't think that's possible in near future, but within each domain, for example, through this KDD cup, we have a large label data set of molecules. Can we train a large graph neural networks and then transfer this to different molecular property prediction tasks as a drug discovery? So.
Right, it's a very interesting perspective, and it seems like we are interested in these molecules, and the social networks are more shallow, shallow gen is good. Do you have any perspective on whether there's any innovation on the, I don't know, like node classification stuff? Because I guess there are some challenges like sampling, or do you think the current ones are enough, or yeah? Any thoughts on that? Basically, currently we have a lot of sampling techniques being proposed, and we kind of noticed that the deep GNN do not really help. But it seems like the current method only trains like 2-layer GNN, maybe increasing to 3-layer can give us some gain, not 100 layers. But like, do you think there's any open challenge in terms of node classification, those large graphs in Facebook or Microsoft, those kind of big graphs?
Is that question for me or for everybody?
For everyone. You can start too, if you have any thoughts.
I think one of our panelists hasn't like finished the first question yet, so that's why I need to.
Oh, right. Yes, then we can probably let's go to Dr. Zheng Zhang, and ask you about the open challenge.
You're muted, Jen.
Can you guys hear me now?
Yeah.
Yeah, let me start by commenting on Ito's earlier comment that how to do the reverse problem. I actually think that's a huge potential area where you extract from unstructured data to structures, right? So sequence is a sequence. Just because you have to say the words writing on a sound wave doesn't mean there's not a structure underneath the text. Say likewise for images, you can think of the 4D tensor, but really it's about objects interacting with each other, and so on and so forth. But a huge amount of structures underlying what I call rendering structures data, and of course the interaction between them. So I think that would open up a lot of new opportunities, which I think this community hasn't been able to look into. On that regard, I think there is a very deep connection to the transformers. If you think of a transformer, I think we did that work very early on. We pointed out that the transformer is really nothing other than a stack of GATs with skip connections, right? It's really what it is. It's arranging the days for, for images, text, and whatnot. And I have seen very little work to connect the two. Though we have as a GN community, have done a lot of theory work on understanding the properties of stacking the GN layers, but we haven't done so much to connecting to, let's say, the transformer work. So I think I start with that. But then I want to comment on, so I think our lab had being at AWS, we not only work with academic, we also work with real customers. And I think a lot of scenarios that the academic setting is not covering. For instance, a graph is never static, right? Tell me there existing one graph that is static. Not only that you will be missing edges, missing nodes, they will appear over time. Some of the graphs are just temporal in nature, a low segment, for instance, or social network. And those are not reflected in our benchmark today, even though, let's say you take a Reddit or product, they all add on the concepts or the connections are edges are, you're taking a final snapshot, you're removing all the temporal data. That is unfortunate, right? So you are actually predicting sometimes the past from the future. So that view has to change, I think, from my perspective. That is, you shouldn't think of graph, static graph. And a graph is never complete, right? You can also always think of a graph is kind of sampled from a ghost graph. So we shouldn't think of like a problem is only graph and node classification or link prediction, because in practice you have to do both, right? So that is missing. That is not reflected in our today's benchmark. And finally, I think the graph is never simple, right? People treat a homogeneous graph, heterogeneous graph, but what we found in real customer scenarios is they often have tabular data. You have foreign keys connect to each other's. And if you talk to any of the internet companies, they often log that data in columns, right? So you have tabular data to begin with. And tabular data is a different animal. And I think our benchmark today are not covering that. And I also think it's rather interesting that it's the applications that are seen widely deployed in industry and the customers are fraud detections, which happen to be the data set the community most lack of because privacy issues, right? So that is something that we're not covering today. So in summary, I just saying, there's this unstructured to structured word that is waiting to be discovered, there's connection to be made, and also the lack of representative real world applications in the benchmark suite. I think I gave a lot, but I hope I don't bore you guys. I shut up.
No, that was really interesting. So you are contributing like the lack of focus on temporal graphs to the lack of benchmark data sets, or do you think like people are just not interested in temporal graphs and do not work on it? Like, what is the reason the research on temporal graphs is not that focused.
I think we're pretending all the graphs are static, which is never true. That is my point.
Yeah, I get
maybe
your point,
molecule graph maybe.
But
God
what
creates
if
the molecule suddenly. Yeah.
But what is the reason like the community ignores the temporal graph problem to some extent?
Oh, I think it's just from system perspective, it's just hard to model, right? In a system perspective, you have to have a different order of accessing the data as you do now. But in DGL or in PyG, we have a lot of optimization, but never took into account of the temporal behavior that much. That is, even when you sample, we need to understand what are the real edges that you want to sample. If there's temporal behaviors, then it constrains how you can sample, for instance. It's just difficult, and also difficult to analyze too, because now you're having a evolving graph that's temporal behavior is different over time. So, and of course, when we talk about time has multiple scale as well, right? It's multi-scale. So that also makes things very interesting and also very challenging. Oh, I should mention, I think the other problem that I see, that is, I actually didn't look at it, the challenge results. I see a lot of applications of pooling in real life. So graph, I should add, is never flat. It's always hierarchical in some way, right? But the hierarchy could be soft, and hierarchy can change from perspectives to different perspectives. And you have all this happening. If you look at recent perceiver, right? This is this kind of clustering. That if you think of the perceiver architecture, it's really putting a pooling internally to the latent space, right? And you probably have multiple of them, which is not the case today, even in the perceiver. I think it's into the early days, but I don't see this. We have diff pool, and there's many follow-up works, but that somehow it's just taper off. Understand, even for the benchmarks, it's very difficult to label hierarchies, but it doesn't mean it's not, right? The cliques, by the way, for instance, for frauds, the cliques is very important to detect. Who are the bad guys? Bad guys usually gang up together, but they gang up together in some interesting ways, but not overly complex that we cannot detect.
Thank you for your insights.
Yeah, thank you so much. Like the temporal graph, temporal information is indeed overlooked. And just by the way, the OGB large scale challenge, the MAG has this year temporal information. And I found all the winners actually exploited the temporal information, either in the sampling of the neighbors, like only sampling the past paper that the paper cites, or use some positional encoding that encodes this temporal information. But of course, it's just at the granularity of year, so it's not so fine grained. And seems like the benchmark is lacking in this area. Thanks for the insight. Very, very great. So yeah, let's then talk about the scalability problem that I just brought up. So like we talked, this molecules have big, like a deep GNN, and for social networks, what do you think is kind of is there anything we should do? Is there any open challenge we should address, given that there are so many techniques being developed? What do you think?
Yeah, for node classification tasks, I think it's very interesting because people realize that in many cases, we can use simpler approach and achieve like almost the same results. So starting from like, for example, simplified GCN, and people later realize that, okay, if we separate the operator, like in the current for example, GN operator, usually we do feature propagation and then the nonlinear transformation, right? But if we separate the two operators in that layer, like we first do feature propagation and concatenate, and then do this nonlinear transformation multiple layers, the results is almost the same or sometimes even better. And the efficiency was much, much faster. So somehow I think the efficiency, right, so also kind of link us to the next thought. What's so important in that traditional like message passing framework in a graph neural network, right? So if later it turns out that if we do the feature extraction in a very nice way, and then later we do the nonlinear transformation, probably problem will be automatically solved. So that's kind of like the biggest dilemma here, right? So what's really important in graph neural network. And in terms of other approaches, like what you mentioned, the sampling approach, right? So we also did something like called Ladies. That's the new actually is the first author for that work. And that kind of technique has been applied to later like heterogeneous network, like the heterogeneous graph transformer, like Yu Xiao is one of the co-author. So we find that sampling definitely is very important. But a similar situation, right? So we realized that in the current leaderboard for the heterogeneous graph and also for the node classification task, the top ones are the methodology that they do not combine the two operators together. Okay, they are the ones like first to do some kind of feature extraction and concatenate, and then do the nonlinear transformation. So then the natural question, like if we want to go deeper, right? So then which part we want to go deeper? This is the later part, I mean the nonlinear transformation part, or like the feature propagation part. Yeah.
Right. It's interesting. Like on all the leaderboard, OGB leaderboard, those shallow like message pass, like a non-linear message passing kind of works better. But on large scale challenge, it seems like a non-linear message passing starts.
Yeah, I checked the OGB. I think no, it's MAG. Okay, I think it's academic graph that one. So like, like 1 week or 2 weeks ago, when I checked the leaderboard, the top one actually, yeah, essentially it's kind of shallow, kind of feature extraction. Yeah, I think that one I'm not sure. In my mind, it's already like a large scale.
Right.
So following Yizhou's point, I just want to add one comment or one more question. So I'm wondering how the panelists think about it. So like in speech or computer vision, we saw when neural networks were first, like deep neural networks were first introduced into this field, this problem space, right? We see a huge jump in terms of performance accuracy, right? So so if my understanding is correct, at least by observation from OGB, we can see that this graph neural networks did improve all the performance on all those tasks, right? But we didn't see the huge jump compared to traditional graph machine learning methods like I don't know, structure feature engineering, right? So I guess first of all, this is my own observation. I guess the first question is, do you think it's true or not? Secondly, if it's true, are we able to see in the near future that graph neural network can bring a big jump for all the graph machine learning tasks, and maybe how we can get there? Yeah.
I think that's a great point. So just to share what I'm thinking about, I think it is true that currently, if you look at, for example, deep learning or images or speech and text, and you compare deep learning with non-deep learning, I think nowadays it's clear that deep learning consistently and significantly outperform non-deep learning, I think nowadays. So I think it's also true that our graphs, so the trend is not that clear, and I think the performance margin is not that large compared to images and text. But I think I still hold the hope that that will happen eventually, our graphs, because if you look at 10 or 15 years back, so at that time, people also do not believe that deep learning will outperform non-deep learning or images or text at all. I think there is, but I'm not sure like what is the problem. I think one thing could be that because just it's deep learning or graphs. Currently, if you look at deep learning or graphs and graph convolution, etc. So I don't think graph convolution is is the methodology for deep learning graphs, because it's basically some kind of extension of a convolution from images graphs. And so I think there might be for example, a new deep learning operational graphs that might help, or it's just because of data or computation, I don't know. But I think looking forward, I still hold the hope that, you know, or one day deep learning will outperform non-deep learning dramatically or graphs. But I do have one point to share. Another point is basically, I think if you look at the images, text, they are all images and text. They are similar, more or less. But if you look at the graphs are very diverse. If you look at the molecular graphs, it's very different with social networks. I do not believe if you pre-train a model or social network, and that could help molecular graphs. But images, what we have been doing is if we work on biological and brain images, if you have a very small number of images in the medical or biological domain, and you don't have much choice, you pre-train your model even on ImageNet, and then you transfer the model to biological and medical images. That helped significantly. But I think in the graph domain, it's much more complicated because these graphs are very different. The molecular graphs, ALP graphs, the social networks are very different. And one thing I'm thinking about is probably we need to somehow approach this in a domain-specific manner.
So okay.
Yeah, sorry. So I guess sorry for I think I changed the question. Also, please feel free to go back to previous question on the scalability issues. Yeah.
So I think that we already said a transformer is nothing but fully connected graph network. We can just say that everything is already graph neural network. Just claim the victory. But jokes set aside, I think the issue, a lot of issue, it has to do. There are missing information that the model is not looking hard enough. For instance, I mentioned that when you do the graph, no classification, you assume all the edges are trusted, and vice versa, which is never true. If you think of even for molecular things, you look at the bond, chemical bond, but they are 3D structures. So there are other connections that we're not capturing. So that's just within the graph, you're not capturing enough stuff. And then we're talking about even at the node level, right? If you're talking about taking an article, you summarize it into a 700 byte-ish embedding, and that is not the right way because different articles have different summaries. So you're starting working with a embedding that is probably off to begin with. So there is a lot of room to improve. I think if we take a simplified view that just look at series itself, right? We actually have a recent paper in ICML. It's a long oral. I encourage people to look at. It's called TROll. Look at how you can go very, very deep. But it was based on a very convenient assumption that you have homogeneous graph and you have the links nodes and have certain structures and you can analyze them. But real world data is never so simple, right? And it has potentials not being modeled per se. So we are just looking at a closet and then we say, hey, we're not looking elsewhere. And that I think itself limits the progress. But to break it away though, I think it's hard. So do you want to actually train a transformer underneath every node and have the back propagation all the way down to the word embedding side or even BPE side? I think that's not clear. On scalability side, I think as speaking from DJL's point of view, right? So we are serving both customers in industry as well as academics. I think the issue I'm facing personally is non-technical. That is, how do we design the right task and challenge enough that fits academic people's budget, right? 4 GPUs, they have maybe 20 gigabytes of GPU memory, right? And you have terabytes of storage. And how far can you scale to? So there is this limit. And the industry is kind of long tail. So there's people's graph is so big, right? You would take a very different architecture to do that. And I don't think that is the right thing for academia to focus on. Anyway, so I think scalability issues, if you look at the practical context, there is a limitation. How do we manage to give you guys the right tools and the right data set? And yet it's not so simplified, yet it reflects real world cases. And yet it would yield insights.
It's a great insight. Yeah, there's some discrepancy between real world data and the simplified academic data. That's a great insight. Jen, do you have any comments on?
Yeah, so I want to go back to Yuxiao's question. I think Shuwan makes a good point. I think in general, graphs are really complicated and also very diverse from each other. Right? So if you compare the graph data with image data, right? So image data, what is the input of image? They are very low level pixels, right? And that's why we can use deep neural network to extract the very high level representation. And that's why in general, a deep neural network can be useful for any kinds of image because the input is a very low level representation. But this is not the case if the data is graph, right? So for graph neural network, the input is the node features and also the graph structure, right? So if the node level features are very high level, right? Then so we may not want to use very deep neural network there, right? And also why graph neural network helps is because we basically use the graph structure to combine to do feature propagation, right? But if in some tasks, if the graph are not so useful, then even you have many layers graph neural network, that will not help the task, right? So I think in general, it really depends on the task. If in some task, if the graph structure is very useful, then we may just need to have a few layers, then that is sufficient, right? But in some tasks, if the graph structure is not useful at all, then we may don't want use graph neural network. And also in some cases, maybe the same case as the latter case, which is the node features is sufficient, right? Then we just need to apply, maybe for example, the node could be an image, right? Then we can just apply deep neural network to the image, right? And then output the node label. So I think in general, for graph classification task, for graph task, I think it's really complicated. It really depends on your understanding of the problem, right? So what would be the most important features for this task? Are the node features very important, or are the graph structure very important? And how to sort of effectively combine them? I think that's actually really key for different tasks.
Yeah, that's a really great insight.
So what's sorry?
Go ahead.
Just one question. What's the reason we only see pre-computed node features in graph neural networks? Is that an issue of scalability, or what is it in your opinion?
Me or I think
you.
Yeah, I think that's made because of the people just using some standard benchmarks, right, to evaluate their algorithms. But I think in practice that shouldn't be the case. I think in practice we should, for the node features, I think we should also start from some low level features. For example, I said for if the node are the images, I think we also have add a encoder on top of the node. But of course, I think there could be some scalability issues there, right? For example, if we have a really big graph of images, right, then you have to deal with the image encoder, which is very deep, and also you have to take care of the graph neural network architecture. I think in general there could be some scalability issues there in practice. But in general, I think in terms of scientific papers, I think right now many people want to just evaluate their performance of their GN architectures, but in practice, I think this shouldn't be the case.
Yeah, thank you.
Well, I think the issue is with if you run a transformer for every, let's say, a paper citation, the computation cost is prohibitive, right? So, but the information is there, because if you just summarize citations link and then summarize one node with one embedding, you lose a lot of context information because you cited the work in some particular paragraph. That's like the anchor text.
Mm-hmm.
And what you cited to, what you cited from, both have the context. So those information, when you simplify it to be just a pretend embedding, you lose that. But on the other hand, if you start with byte BPE, like a byte representation for tokens, you're also starting from a too big, too wide a landscape, too low levels. But there has to be some way to link the two. I haven't got around to actually do that. And it's going to be a different game, right? So how I'm going to ask my students to try that if the OGB benchmark is not set up that way. That would be suicidal, right? But that should be the right way to do it. Let me just say that.
It's a great point. Yes, indeed, some of our tasks are designed, are kind of simplified to fit into the current GraphML literature. But of course, there are a lot of information we are not utilizing, and we are just focusing on one aspect. And really great point. Next, I want to move on to the next topic, which is unrelated. So the question is, what is the good benchmark for evaluating the progress in graph machine learning? So like OGB has been trying to build common benchmark for GraphML, but as we discussed, we also have some limitations of the current benchmark. And yeah, any thoughts on what would be the good benchmark to for the next few years to evaluate our graph machine learning models?
Yeah, so I think many of the panelists have mentioned that graphs, including Xiuwang, right? So you talked about for graphs in different domains, actually semantic meaning are quite different. So for example, the node, right, they are different and they have different features. And for the links, for social network, I think it's closer to, for example, the manifold, meaning that the link indicates the similarity. But in some other cases, right, so the link actually means different things. For example, chemical bond, right, so it means different things. And in some heterogeneous network or this large graph, right, the link means different things. So we probably wanted to first try to partition the graphs into different domains, right? So that's then also, under that framework, then we can talk about whether different domains of graph can help each other. But within that particular domain, we can first know that whether we need some very specified, very special designed graph neural networks. And the second thing I am thinking is the tasks we also need to make more categories. Right now, I think we just have node classification, link prediction, and graph classification or regression. But probably should add more because there are so many graph problems. Before graph neural networks, there are so many graph problems. They are not fall in the regime of all those three categories. For example, we want to just do graph similarity search. We want to do a kind of subgraph isomorphism test. We wanted to find the most critical nodes in the graph. So for this one, okay, I want to say more about this task. So for this one, it sounds like node classification, but it's different from the node classification that we have seen, right? Which most likely just depends on local neighborhood or majorly your own information. If you already know enough your own information, your features is not missing or very complete, probably it's good enough. But for this kind of critical nodes detection problem, it's for example, I want to know by removing what kind of nodes, then the network structure will be maximally disjoint. So it really carries the kind of global information of the whole graph, right? So that's why even it's a node level, but it's not the node level that we were talking about before. It really carries the global graph information. So that's why I think we should add those very interesting and very challenging, most of them are NP hard kind of graph tasks into our graph benchmark data set. So I before I end, I want to add a story. So we were talking about whether we should combine the graph feature and feature propagation and nonlinear transformation together. So then according to our study, okay, so for node classification, probably we can just separate the two. But for the graph classification, right, it depends. So if we just do graph classification for the molecular data, we separate the two operators still beneficial. But if we just treat the image itself as graph, then we realize that, okay, the two operators has to be together. If you separate the two, like do the feature propagation first and then do nonlinear transformation next, then it will not work. Okay, it's not as good as the deep learning methods in the images. So that probably explains something, right? Maybe in the image classification, okay, we really need to capture the global property, but for the current graph classification for like molecular, we only need to pay some attention to maybe some spatial nodes. That's just a collection of nodes. We really need to understand the global property of that graph. Then we can do the graph classification. But in order to really understand that, we really need to go to a specific domain, right? So we try to understand, oh, for this molecular classification task, indeed, we just need to identify those couple of like atoms. Okay, so if we identify those atoms, then it will have that kind of property. But for some like molecular problem, maybe we need to identify some subgraph. In that case, maybe, right, so this kind of combination of two operators becomes so important. Yeah, so that's my 2 cents.
Yeah, thank you for the insight. Very interesting. There are different domains where like optimal things could be different. Any other thoughts from? Yes, go ahead.
I think when we started out in the deep learning, there was MNIST, right? And it's saturated. And then people move on to ImageNet and saturated. Well, not so saturated, but people know a little bit. And then COCO and VQA, all those. And you from MLP have PTB and all those more and more benchmarks. So the question is, are we exhausting our existing benchmarks so that we need to move on? I don't know. I think this is a very good open question. I mentioned earlier that I think our benchmark is not complete. I think the graph is never static. The graph, of course, is never complete. Right? The graph is never simple. For instance, tabular data. So those data set, I think, are in terms of graphs characteristics are missing already. That's something to look into. But also the tasks. Very important tasks in the domain of knowledge discovery. And I think that goes on to other important applications like community mining and so on, is related to graph matching, subgraph queries, which asks you to think about, you might want to embed the graph differently such that you can serve query easily, right? It's not you have a different way because the task demands that. Query toolbox. I think that is one example. You make the geometry easy for you to do first logic operators, things like that. But I think that's important in real world scenarios, but also scientifically it's important. You can think of designing new search engine that way. Anyway, so that subgraph and community mining I mentioned, hierarchical mining, those are very important, I think, hidden attributes, even in today's benchmarks, even today's data set. It's just that, but they are not measured. So that's one thing that we think, I think we should look into. Yeah.
Right. Yeah, I agree. with you.
I think in general, we're gonna see more and more benchmarks on graphs, considering that a graph are very ubiquitous, and then now you see like really there are many areas we can use graph network, right? For example, like biology, physics, right? Even chemistry. So we really see a lot of applications. So one particular benchmark I want to mention is actually the Open Catalyst discovery project initiated by maybe you guys you already know that, like initiated by Facebook and also CMU, right? So that's, I think, is a really big project focused on like material discovery, right? So I think the label really a large data set based on the DFT density function theory, right? And with that data set, I think this allows people to work on like material discovery. I think Shuiwan also sort of like, I think I saw you also work on that, right? So and also this, I think also this actually basically something I want to mention, like maybe for the future direction, because right now for graph neural network, we mainly apply graph neural to graphs, right? But then in real world, like many data, like for example, molecules, I mean they can be represented as graph, but then a more natural and also intrinsic representation for molecules also like it's actually the 3D structures, right? And then we can actually apply graph neural network to do neural massive parsing on 3D structures. So I think like for molecule property prediction, a really promising direction in the future is really trying to do massive parsing on top of the 3D structure. I think there are already many exciting work along this direction. For example, the SHNet, DNet, right, and also Shuiwan also has paper on this, which is SphereNet, right. So in general, I feel like applications in drug discovery and also material discovery, we're gonna see a lot of like potential for graph neural network, or even like we can say like geometric deep learning.
Actually, I think you know, probably Faye should do the same. I did it for 3 months, looking at a citation to the framework and see where they are coming from. It was very surprising and very interesting. I mean, it's sort of long tail, but of course we know the whatever the OGB database set is, where they're from. But there are mechanical engineering, I think Jan mentioned, but also high energy physics is using this a lot. Drug discovery, circuit design, and civil engineer, neuroscience. If you think of the EEG signals from your head, right? People use this to model the whatever going on in your head. Neuroscience, that is to say. I think I categorize like 20 something. You know, it's and there are a combination of them. It's very surprising how people use them. In speech recognition, for instance, there's something called a diarization. That is, you have a sound wave and you want to map it to a certain person, right? You map to certain roles. You want to have the audio track. You want to separate them and say who is saying what. It turns out to be a graph problem, right? And of course, when you do tracking, you have faces coming in here that you want to identify the persons in different frames. It turns out to be a graph problem. So there's a wide range of you know, applications out there. I think it's not yet in. Now the problem is, I look at some of the HEP, high energy physics paper. I understand nothing of it. It's just too difficult for me. I just mentioned, oh, okay, so they use DGL. Okay, cool. But I have no idea why they use that. They did mention it's not the only method. It is one of the methods that actually gives a performance boost, which is glad to know. But anyways, I think in terms of application, there are many domains that's out there.
Okay, great. I think I just echo what has been mentioned by other panelists, especially Yizhou and Jie. I think I still think that the graph is just much more complicated than all the images and the text, because images, they're just low-level pixels, and text, they are just sentences, etc. And whether you are talking about the food or sports, you know, it has to be a sentence, or if you are taking image of a natural image, it's just compared to microscope images, they are just physical information from the real world. It just either you take at a certain level, either it's at a micro level or macro level. I think, but the graphs are very different and much more complicated. I think that's why one of the reasons why we haven't advanced to the point where we can train a single graph model which can be used in many different places. And I don't know if that's eventually going to be possible, but I think it's very hard at this stage. I think for benchmarks, I think it's very important to understand fundamentally what are the differences that this graph can capture and somehow characterize this data set benchmarks in different ways. For example, I think for some of the graph data, I think Yizhou already mentioned, the edges mean similarity. If I have two nodes that are connected by edge, I think there is a smoothness assumption that the labels should be similar, but in other types of graphs, I think they call this disassociative graph, where the nodes if two nodes are close, that doesn't mean their labels should be similar. And we actually have proved that if you use that assumption, it just hurts the performance. I think the graph is just very complicated. We might need to think fundamentally what is their difference and somehow categorize their challenges in different ways. The challenges for different graphs might be very different. Yeah, I think Jia mentioned this molecular graphs. The challenge here is that, for this open catalyst, they give the coordinates of these molecules, and we need to predict the energy, etc. So I think one essential challenge is how can you make use of this geometric information in the message passing process. In other molecular prediction tasks, like the one here in KDD cup, so you are given the molecular graphs, not the 3D, and you need to predict something that is related to 3D. And I think the KDD cup organizers, Weihua and Yuxiao, has made this a very interesting problem. So how can you make predictions that depends on 3D information, but you are not given 3D information. And if you try to compute 3D information, it will exceed the timing budget for sure 100%. So I talked to actually, Peter reached out to me, and we had some discussions that we feel pretty much the same way. So if you try to compute 3D information out of this 2D molecular graphs, that if you can make it very accurate, and it will for sure help the prediction of the energy. But if you make it accurate enough, so your time budget will exceed the required budget for sure. But if you use some fast method to compute it, so and you will not exceed the timing budget, but the structure is not accurate enough. And I think, as Larry mentioned, if the structure is not very accurate, it will not help. If there is a slight difference in terms of the geometry, that will not help with energy prediction. I think really the challenge here is very different.
Right. That's a great point. And for that, for the next update of this large scale challenge, we're going to provide 3D information for the training molecules. So, but for test molecule, we want to give 3D information, and that could give some supervision signal. But yeah, it's really great point that QM9 is actually not so realistic, given that we actually need to obtain 3D information, and that's very expensive in the first place. So that's, I think, something to note. But it's really interesting to hear a lot of opinions on different domains have an interesting problem that the current benchmark did not really cover, and different domains have different optimal modeling strategies. And it's indeed very interesting to cover those domains. Thank you very much. So finally, I think we only have 3 minutes, but let me ask a final question. It's a very broad question. What would be the ImageNet moment for graph machine learning, in your opinion? What domain will impress the community, broader community, that graph ML has achieved the ImageNet moment?
You mean which application, or?
Like any applications of graph machine learning.
Yeah, maybe I'm biased because right now I'm mainly interested in drug discovery. So I would say maybe drug discovery is the most exciting area for graph machine learning. Right.
Is there anything that you think, once you achieve this, people will?
Yeah, so I think, because now I'm collaborating with people doing hardware and also material science, I think maybe, yeah, so if we can have some breakthrough in those two domains, it's also going to be very exciting.
Are there kind of common benchmark like ImageNet on each of the drug discovery and hardware community, like CASP challenge or something like that in drug discovery, or something that you can claim, it's fantastic, or something?
It's not that unified. I mean, nobody has created something called ImageNet yet. So even within material science, for example, because they do not pay attention to the data collection previously, so it's like very scattered. I'm not sure like who is going to take the responsibility. Maybe most likely it's not from computer science, but who in material science want to do that. Jay, you mentioned that that challenge. Maybe they have already done something on that.
You mean for drug discovery?
Material science. I think you mentioned the Facebook.
Yeah, material discovery. I think that mainly the open catalyst discovery project. I think so. There's a big data set there. I think people have been, there's quite a lot of like interest there. And then in terms of drug discovery, so I think there are mainly two groups. Actually, one is from my group. So we just released an open source machine learning platform for drug discovery. So in our project, which is called like a drug. So in our project, so basically we benchmark like a bunch of different tasks in drug discovery. So this is the one. So another one is also, I think it's called like, I forgot the name, is initiated by, maybe you know, like a Marinka's group, right? So they have I forgot the name of the project. So basically they provide the data sets of a bunch of different tasks in drug discovery. Right.
Yeah, data commons. Yeah, the
data commons. Right.
TC.
Yeah, so mainly I think now in the domain of drug discovery, there are many like, and also I think in Shrivon's like a group, but Shrivon also like released a platform on graph machine learning. I think mainly also focus on molecules, right?
Yeah, I think. Yeah, you go ahead, Joe.
Let me try to make a different sound. I think, however, I like very much our drug discovery. I actually started out with that direction too, at least one of them. I think drug discovery is $10 billion in 10 years kind of business, right? So the AI portion, unfortunately, is a very small one out of the whole pipeline. The human trials and all those are very costly. So however we like it, I personally don't think the ImageNet aha moment will be in the drug discovery. Sorry, Jen. To disappoint you, but that's my bet. I think the ImageNet moment will come when the unstructured problems are solved in graph way. That is to say, today's transformer or whatever, the CV or computer vision or reinforcement learning, those hard problems are being structured. If you think of the reinforcement learning, if you have a model, even in the latent space that is graph, that is really a word model, then you can make the training much efficient. Think of NLP all these NLP problems, the natural language understanding problems, the retrieval problems, computer vision problems. Today, they are all solved in a brute force way, pretty much. I think if we can solve that in a structured way, that would be the really aha moment. But I may be wrong. I mean, drug discovery may be great. Maybe there's something else like chip design or whatnot, right? That can light it up. I don't know. I just think that there are a big word out there for all the benchmark we're seeing, all the tasks we're seeing, there are potentials. But given the question is, what is ImageNet moment, which is a tall order to think about. I'm not sure I see it there. But I'll be very glad that I'm wrong. I'll be wrong.
No, thank you for providing insight. Very interesting.
Yeah, just briefly, I think my opinion again could be biased, and I worked on more on fundamental science. I think, for example, we do this we use deep learning for molecular graphs, for material property for different areas, and for this, even for this open catalyst that Larry just talked about this morning. I think the key of this is essentially we are solving a quantum system. Basically, we are dealing with a quantum system of atoms and electrons, and if we really want to solve this exactly, I think there is a way to do it. That's basically you solve the Schrödinger equation, and the complexity is if you have a system of n particles, your complexity will be of the order of power 2 to the n. I think we can currently solve up to probably about 17 particles. And all we try to do this DFT, I think, is the approximation of the Schrödinger equation. And now we are using deep learning to approximate DFT. I think eventually all will come together. Essentially, it comes down to if we are dealing with problems in medicine, in material science, in chemistry. I think the key is essentially to accelerate the solving the equation we're still using deep learning. I think. Thank you.
Yeah, thank you. Yeah, it's very interesting. Applying GNN for simulations, very promising. So I think we are actually 4 minutes over time. So thank you everyone for staying here and joining the panel. I think we can conclude here.